4 billion years ago, Mars had oceans, a thick atmosphere, possibly even life. Then something went catastrophically wrong. And for decades, the smartest people on the planet have been asking the same question: can we make it home? Could we actually bring Mars back? And if we could, should we? If you want to understand not just the headlines but the actual science underneath them, make sure to give this video a like. Now let's get started. Mars sits at an average distance of about 228 million kilometers from the Sun. That is roughly 1.5 times farther than Earth. Because of that distance, Mars only receives about 43% of the solar energy that hits our planet. Less sunlight means less warmth. The average surface temperature on Mars is around -60 degrees Celsius, 60 degrees below zero, and that is the average. At the poles in winter, it can plunge to -125 degrees Celsius. For comparison, the coldest natural temperature ever recorded on Earth was -89.2 degrees Celsius in Antarctica in 1983. Mars makes that look mild. The atmosphere on Mars is about 95% carbon dioxide. Sounds like a lot of greenhouse gas, right? The kind of thing that should warm the planet up. Except the atmosphere is so incredibly thin, less than 1% of Earth's atmospheric pressure, that even all that carbon dioxide barely does anything. It is like trying to insulate your house with a single sheet of paper. The molecules are there, but there are just not enough of them to trap meaningful heat, and then there is the gravity. Mars has a gravitational pull that is only about 38% of Earth's. That means if you weigh 70 kilograms here, you would weigh about 27 kilograms on Mars. That sounds fun at first, but low gravity has brutal consequences for biology. Long-duration studies of astronauts aboard the International Space Station, some spending up to a year in microgravity, have shown serious deterioration in bone density, muscle mass, vision, and even the structure of the brain.
No.
Mars gravity is better than zero gravity, but we genuinely do not know if it is enough for humans to survive long-term. We have never tested it. No one has ever lived in 38% gravity for a year. We are stepping into biological unknown territory before we have even talked about the atmosphere. So that is what we are working with, a freezing, thin-aired, low-gravity world bathed in radiation, sitting further from the Sun than we are used to. And yet, people are seriously, methodically, scientifically working on changing all of that. Why? Because Mars is the closest thing to a second home that we have. Venus is closer, but is basically a hellscape. Surface temperatures hot enough to melt lead, pressure that would crush a submarine, clouds of sulfuric acid. The Moon has no atmosphere and no protection. Mars, for all its hostility, has water ice. It has a day that is only 40 minutes longer than ours. It has seasons. It has a surface area roughly equal to all the land on Earth. It is harsh, but it is not impossible. At least, that is the hope. Now, terraforming, and this is a word you should sit with for a second, comes from the Latin word a terra, meaning earth, and forma, meaning shape. To terraform is to earth shape. To take another world and sculpt it, over time, into something more like home. The concept was popularized in science fiction for decades before scientists started treating it as a legitimate long-term engineering goal. The planetary scientist Carl Sagan, one of the greatest scientific communicators who ever lived, proposed in 1973 that we could terraform Venus by seeding its atmosphere with algae. He was among the first serious scientists to treat planetary engineering not as fantasy, but as a question worth studying. For Mars specifically, the conversation has evolved enormously over the past 50 years. Early proposals were almost charmingly naive, just nuke the polar ice caps and let the carbon dioxide do the rest. That idea, famously floated by Elon Musk in 2015, still gets attention. But the science behind it has been heavily scrutinized since then, And the picture that emerges is far more complicated than dropping a few thermonuclear bombs and waiting. The reason goes back to that 2018 study. Even nuclear detonations at the poles would not release nearly enough carbon dioxide to meaningfully thicken the atmosphere. The reserves simply are not there in the quantities we once hoped. So if raw carbon dioxide is off the table as our main tool, what else do we have? This is where it gets genuinely fascinating. Scientists have proposed using super greenhouse gases, synthetic chemicals far more powerful than carbon dioxide at trapping heat, and manufacturing them on Mars from materials already present there. Compounds like perfluorocarbons, which are thousands of times more effective as greenhouse gases than carbon dioxide, molecule for molecule. In theory, factories on the Martian surface could produce enough of these gases to gradually warm the planet. The physicist Robert Zubrin, one of the most vocal advocates for Mars colonization and co-founder of the Mars Society, has championed this approach. His vision involves a step-by-step process. First warm the planet, then release the frozen water, then introduce microbial life to begin producing oxygen over geological timescales. It sounds almost manageable when you lay it out like that, almost. But there is a problem that no greenhouse gas, no nuclear bomb, and no factory can fix. And it is arguably the most fundamental obstacle of all. It is the reason Mars is the way it is in the first place. And it is not something we can engineer around with technology we currently possess. We are talking about the magnetic field, or rather, the catastrophic lack of one. 4 billion years ago, Mars had a magnetic field. Scientists know this because ancient Martian rocks, studied both by rovers on the surface and meteorites that landed on Earth, show traces of magnetization, minerals that locked in the direction of a magnetic field when they solidified, like a fossil record of planetary physics. Mars once had a dynamic, molten iron core generating a magnetic shield around the whole planet. And if that had lasted, if Mars had held onto that field, it might have held onto its atmosphere, its liquid water, possibly even its chance at life. The story of Mars and the story of Earth might have been very different, but the core cooled. Mars is smaller than Earth, about half the diameter, and smaller planets lose their internal heat faster. The dynamo that generated the magnetic field switched off somewhere around 3.7 to 4 billion years ago, and without that field, something relentless and invisible moved in to strip the planet bare: the solar wind. If you have ever wondered not just whether we can terraform Mars, but how long it would realistically take humans to actually establish a civilization there, the infrastructure, the generations, the timeline, I covered all of that in depth in the video on the card above. It pairs perfectly with this one. Go check it out after we are done. The link is in the description and pinned on the comments. Now back to the solar wind. The sun is not just a light source, it is constantly exhaling. Every second, it ejects billions of tons of charged particles outward in all directions at speeds of around 400 to 800 kilometers per second. Here on Earth, our magnetic field deflects most of this stream. You can actually see it happen at the poles, where the particles that do get through interact with our upper atmosphere and create the auroras. That magnetic shield is why Earth still has an atmosphere after 4.5 billion years. It is why our oceans did not evaporate into space. It is, in a very literal sense, the reason you are alive to watch this video. Mars has no such shield. So the solar wind hits the upper atmosphere directly, and it does something called atmospheric sputtering. It physically knocks atmospheric molecules off the planet, one by one, over millions of years, and NASA sent a spacecraft specifically to measure this. The MAVEN mission, which stands for Mars Atmosphere and Volatile Evolution, arrived at Mars in September 2014 and has been collecting data ever since. What it found confirmed the worst fears. Mars is losing roughly 100 grams of atmosphere per second to the solar wind. That sounds small, but multiplied over geological time, it explains everything. That is how a world that once had liquid water on its surface, a thicker atmosphere, and possibly the conditions for life, became the frozen, barren desert we see today. So here is the question that should be burning in your mind right now. If the solar wind stripped Mars of its atmosphere once, what is to stop it from doing the exact same thing again, even if we somehow managed to terraform the planet? What is the point of building a new atmosphere if the sun is just going to blow it away? That question, and the answers scientists are actually working on, is where this story gets truly extraordinary, because the solutions being proposed are not small, they are not subtle. They involve reshaping the magnetic environment of an entire planet. And one of the most serious proposals involves something sitting right at the edge of science and science fiction, something that, incredibly, NASA scientists have already run the math on. We will get there, but first, we need to understand something about Mars that almost nobody talks about, something that was discovered just a few years ago and completely changed how scientists think about what Mars might once have been and what it might still hold beneath its surface today. In July of 2018, the European Space Agency dropped a bombshell. Scientists working with data from the MARSIS radar instrument aboard the Mars Express orbiter, a spacecraft that had been quietly circling Mars since 2003, announced something that sent shockwaves through the planetary science community. Buried under about 1.5 kilometers of Martian south polar ice, they had detected what appeared to be a stable body of liquid water, not frost, not ice, liquid water, a subglacial lake roughly 20 kilometers across, sitting in the dark and cold. Beneath all that frozen weight, the world noticed headlines everywhere. But what those headlines mostly missed was the deeper implication, the one that scientists immediately started wrestling with, because liquid water that far underground, in temperatures that cold, should not be liquid at all. At that depth, under that much ice, the temperature is estimated to be around -68 degrees Celsius. Water freezes at zero, so how is it still liquid? The leading explanation is perchlorate salts. Mars is absolutely loaded with them. Perchlorates have been detected across the Martian surface by the Phoenix lander in 2008 and confirmed by the Curiosity rover in Gale Crater. These salts are extraordinarily effective at lowering the freezing point of water, a process called freezing point depression. Dissolved in high enough concentrations, they can keep water liquid at temperatures far below what would normally be possible. So what you likely have down there is not clean fresh water. It is a dense, bitterly cold, highly saline brine, the kind of environment that even on Earth only the hardiest microorganisms can survive in. But here is where it connects to the terraforming story in a way that is easy to miss. That water, however salty, however cold, represents a reservoir, a hidden supply that has persisted on Mars for potentially millions of years, shielded from the solar wind by all that ice above it. And since 2018, subsequent radar studies have suggested this might not be an isolated case. A 2020 study published in Nature Astronomy identified multiple additional radar-bright regions near the South Pole, potential signs of more subsurface water bodies. The picture emerging is one of Mars as a world that has not lost all its water. It has just hidden it, buried it, locked it away beneath kilometers of frozen ground. For terraforming, this matters enormously. One of the central challenges in any Mars transformation plan is sourcing enough water to eventually cover meaningful portions of the surface, to feed a thickening atmosphere with water vapor, to support biological processes, to create the conditions where liquid water can exist on the surface again. If Mars has significant subsurface water reserves, that changes the inventory. It does not solve everything, but it shifts the equation, and water is not the only thing hiding beneath the surface. Curiosity rover data, combined with orbital measurements from Mars Reconnaissance Orbiter, has suggested that vast deposits of carbon dioxide ice exist buried beneath the south polar layered terrain, in addition to the dry ice we can see at the surface. Some estimates, though contested, have suggested these buried reserves could be substantial. If accessible, releasing that carbon dioxide could contribute something, not enough on its own, as we established, but something to the atmospheric thickening process. The broader picture here is of a Mars that is more resource-rich than it looks from orbit. A world that has, in a sense, been hoarding the very ingredients that terraforming would need. The challenge is not just finding those resources, it is accessing them, mobilizing them, and doing so at a scale that is almost incomprehensible. Let us talk about scale for a moment, because this is where the imagination tends to short-circuit, to raise Mars's atmospheric pressure to something even approaching survivable levels, not Earth level, but enough for plants to potentially grow in open environments, enough to allow liquid water to exist on the surface. Scientists estimate you would need to increase the total atmospheric mass of the planet by a factor of somewhere between 10 and 100, depending on the target pressure. Right now, the Martian atmosphere has a total mass of about 2.5 times 10 to the power of 16 kilograms. That is 25 quadrillion kilograms of atmosphere. To get to even 10% of Earth's atmospheric pressure, you would need to add something in the range of another 160 quadrillion kilograms of gas. Where does that gas come from? From the ice, from the rocks, from synthetic production, from imported comets and asteroids? Yes, that is actually one of the proposals, or from some combination of all of the above. The comet redirection idea, sometimes called targeted impactors, involves nudging volatile-rich bodies from the outer solar system onto collision courses with Mars. Each impact would deliver water, carbon dioxide, ammonia, and other compounds directly to the planet. Some proposals have suggested that a sustained bombardment campaign over centuries could meaningfully contribute to atmospheric thickening. The astrophysicist and author Martin did some of the earliest serious mathematical modeling on this approach back in the 1980s and 90s, and while the logistics are staggering, the physics is not fundamentally forbidden. But here is the honest truth. Redirecting comets is not something humanity can do today, not even close. Our ability to nudge small asteroids is only just emerging. NASA's DART mission in 2022 successfully changed the orbit of the asteroid Dimorphos by colliding a spacecraft into it at high speed, proving the concept of kinetic impactors for planetary defense. That was a genuine breakthrough, but Dimorphos is a small asteroid, and the change in its orbit was measured in minutes. Scaling that up to redirecting a comet the size of a small city from the outer solar system onto a precise trajectory to Mars, we are talking about engineering capability that is generations away, if it is achievable at all. So, where does that leave us in the near term? What can we actually do with the tools and knowledge available to us now, or in the next few decades? This is where the conversation splits into two very different camps, and the tension between them reveals something profound about how we think about planetary science, ethics, and our own future as a species. On one side, you have the incrementalists, the people who say, look, full terraforming is a 10,000-year project at minimum. We should not pretend otherwise. Instead, let us focus on what we can do in the next 100 years. Establishing permanent habitats, learning to extract resources from the Martian environment, developing closed-loop life support systems, building an understanding of Martian geology and biology that we simply do not have yet. This camp tends to be cautious, methodical, and deeply aware of how many unknowns remain. It includes a significant portion of the mainstream planetary science community. On the other side, you have the accelerationists, thinkers and engineers who believe that with sufficient ambition and investment, the timeline can be compressed dramatically. Elon Musk has spoken publicly about wanting to make Mars self-sustaining within this century. Robert Zubrin and the Mars Society have outlined detailed plans for beginning the warming process within decades using synthetic greenhouse gases. These voices tend to be more optimistic about human ingenuity and more willing to accept uncertainty as the price of action. The debate between these camps is not just technical, it is philosophical. And there is a third voice in the room that often gets drowned out, one that asks a question that makes a lot of engineers deeply uncomfortable. Should we terraform Mars at all? Not can we, not how would we, but should we? Because here is something that should genuinely give you pause. We have not conclusively proven that Mars is lifeless. Yes, the surface is hostile. Yes, decades of rovers and landers have not found direct evidence of living organisms, but those rovers have sampled a tiny fraction of the Martian surface, the subsurface where that liquid water sits, where temperatures are warmer, where ancient hydrothermal systems may have once created pockets of habitability, has barely been explored at all. In 2021, a paper published in the journal Astrobiology by researchers including Alexis Rodriguez at the Planetary Science Institute proposed that some regions of Mars might harbor environments warm and wet enough, even today, to support microbial life. These are not fringe ideas, they are published, peer-reviewed science. And if there is life on Mars, even microbial, even buried kilometers underground, terraforming the planet could wipe it out before we even knew it was there. Think about what that would mean. Mars would not be an empty canvas waiting to be painted. It would be a world with its own story, possibly its own biology, that we would be overwriting with ours. The ethical weight of that possibility is staggering. Carl Sagan himself wrestled with it. In his book, Pale Blue Dot, published in 1994, he wrote that if Mars has life, we should not disturb it, that we would have no right. But he also acknowledged the counter-argument that if Mars is truly dead, then doing nothing is its own kind of waste. A planet that could host life, left empty, when life needs somewhere to go. This tension between planetary protection and planetary ambition has no easy resolution, and it is one of the most important conversations humanity needs to have before we start moving seriously toward Mars. Because once you begin releasing greenhouse gases into a Martian atmosphere, you cannot take it back. Once you start warming the planet, you are committed to a process that will unfold over timescales longer than recorded human history. So what do scientists think the actual timeline looks like if we committed fully to terraforming Mars starting today? The honest answer is, nobody really knows. The estimates vary wildly, and they depend on which technologies you assume will be available, which resources turn out to exist on Mars, and how aggressively you are willing to pursue the project. But some rough benchmarks have been proposed in the scientific literature. The initial warming phase, raising average surface temperatures by enough to start releasing frozen gases and melting some polar ice, could potentially take between 100 and 1,000 years, depending on the methods used. The atmospheric thickening phase, getting pressure high enough for liquid water to be stable on the surface, might take anywhere from 1,000 to 100,000 years, creating an atmosphere breathable without a pressure suit, but still requiring supplemental oxygen, could take tens of thousands of years. And producing an atmosphere where humans can breathe freely outside with no equipment at all. Some estimates put that at over 100,000 years. Others say it is simply not achievable with Mars as it is because of that magnetic field problem, and we keep coming back to that. The magnetic field. Every conversation about terraforming Mars eventually circles back to it, because without solving that problem, everything else you build, every molecule of atmosphere you generate, every degree of warming you achieve is vulnerable. The solar wind is patient. It has been stripping Mars for billions of years. It will keep stripping it for billions more. So when a NASA scientist stands up at a conference and proposes creating an artificial magnetic shield for Mars, not in a science fiction novel, but in a peer-reviewed presentation, that is the moment the story shifts from ambitious to extraordinary. In 2017, a team led by Jim Green, who was at the time NASA's director of planetary science and one of the most respected figures in the field, presented a proposal at the Planetary Science Vision 2050 workshop. The idea was to place a large magnetic dipole shield, essentially a massive artificial magnet, at the Mars L1 Lagrange point. That is a gravitationally stable location between Mars and the Sun, about 1.08 million kilometers from the planet, where an object can maintain a fixed position relative to both bodies with minimal fuel expenditure. The shield would generate an artificial magnetic field around itself, one strong enough, according to their calculations, to partially deflect the solar wind before it reached the Martian atmosphere. Not a perfect solution, not a complete replication of what Earth's core provides naturally, but potentially enough to dramatically reduce atmospheric loss rates and give any terraforming effort a fighting chance. Jim Green and his colleagues calculated that within a relatively short period after the shield was deployed, potentially as few as several years, the atmospheric pressure on Mars could begin to rise noticeably as the planet stopped bleeding gas into space. They estimated that over time, perhaps as much as 4 degrees Celsius of warming could result from the reduced atmospheric stripping alone, as a thicker atmosphere traps more heat. The technology to build such a shield does not currently exist. The engineering challenges are enormous, but the physics, according to Green's team, is not forbidden. It is not magic. It is an engineering problem, a very, very hard one, but an engineering problem nonetheless. And in science, it is an engineering problem is actually a kind of hope, because here is what the history of science teaches us over and over again. The things we once thought were impossible have a habit of becoming inevitable. Heavier than air flight was impossible until it was not. Getting to the moon was impossible until we did it in 8 years from a standing start. Mapping the human genome was impossible until we did it ahead of schedule. The boundaries of what humanity can engineer have moved in one direction consistently, outward. That does not mean terraforming Mars is guaranteed. It does not mean the timeline is short or the obstacles are small, but it means that dismissing it as pure fantasy, the way some serious scientists still do, may itself be a failure of imagination. And imagination, as we are about to see, is exactly what drives the next phase of this story. Because there is a concept in planetary science called paraterraforming, and it offers a middle path between the impossible timescale of full terraforming and the fragility of domed habitats. It is a compromise between the cosmos and the colony, and it may be the most realistic near-term vision of a livable Mars that anyone has proposed. Imagine you could not afford to heat your entire house. The winters are brutal, the walls are thin, and the energy required to warm every room is simply beyond what you have available. So instead, you do something smarter. You seal off one room, you insulate it perfectly. You heat just that space, and you live well inside it while the rest of the house stays frozen. You are not solving the whole problem, but you are surviving, and over time, as you save resources and develop better tools, you expand. Another room, then another wing, then one day, maybe, the whole house. That is paraterraforming, and it is not a metaphor that scientists use casually. It is a genuinely serious engineering framework that has been discussed in planetary science literature since the 1980s, when the British scientist Richard Taylor first outlined the concept in a paper published in the Journal of the British Interplanetary Society in 1992. The idea is straightforward in principle, staggeringly complex in execution. Instead of attempting to transform the entire Martian atmosphere, a process that could take tens of thousands to hundreds of thousands of years, you build sealed, pressurized environments on the surface and gradually expand them over time. Not just habitats, not just domes, entire enclosed regions, valleys, craters, eventually canyon systems, and Mars, it turns out, is extraordinarily well suited to this approach in ways that feel almost too convenient. Take Valles Marineris. If you have seen any image of Mars from orbit, you have probably seen it. The enormous scar running along the Martian equator, a canyon system so vast that it makes the Grand Canyon look like a ditch. Valles Marineris stretches for approximately 4,000 kilometers in length. In places it is up to 7 kilometers deep. Its total width reaches up to 600 kilometers across. If you dropped it onto Earth, it would stretch from the west coast of the United States to the east coast, with room to spare. It is not one canyon, it is a complex of interconnected chasms, valleys, and collapse features that together form the largest canyon system in the known solar system. Now here is the extraordinary part. Because Valles Marineris sits relatively close to the Martian equator, it receives more solar energy than the poles, important for any future power generation. Its depth means the atmospheric pressure at the canyon floor is higher than at the surface, not dramatically, but measurably, and its enclosed geography makes it a genuinely compelling candidate for large-scale habitat construction. Scientists and engineers have speculated, carefully, based on real topographic data from Mars Reconnaissance Orbiter's high-rise camera, that sealing portions of Valles Marineris with an enormous transparent enclosure could, over time, create a pressurized environment where more complex life support becomes possible. The sheer scale of such an engineering project is almost beyond comprehension, but it is not physically impossible. The materials science challenges, the pressure management challenges, the radiation shielding challenges, all immense, all real, but none of them violate any laws of physics. And there are other candidates beyond Valles Marineris. Impact craters, of which Mars has thousands, offer natural bowl-shaped topography that could theoretically be sealed with dome structures of various sizes. The Hellas Basin, the largest impact crater in the solar system at roughly 2,300 kilometers across and over 7 kilometers deep, has atmospheric pressure at its floor that is actually the highest anywhere on Mars, approaching 1,100 pascals compared to the average of about 600 across the rest of the surface, still nowhere near Earth's 101,300 pascals, but the highest available. Temperatures in Hellas also tend to be warmer than the average Martian surface because of that depth. It is, in a strange way, the most hospitable natural environment on Mars, even though it is also one of the most extreme. The para-terraforming vision, then, is not about giving up on full planetary transformation. It is about doing something useful and survivable now, while the longer timescale processes play out in the background. You build enclosed habitats. You begin releasing greenhouse gases to warm the planet. You introduce pioneer organisms, microbes engineered or selected to survive Martian conditions, to begin the slow biological work of producing oxygen and breaking down rocks. And inside your sealed environments, human life continues, grows, develops the technology and the knowledge needed for the next phase. Generation by generation, the enclosed world expands and the outside world slowly changes. This vision of overlapping timescales of biology and engineering working together, of patience measured in centuries, is what serious Mars scientists actually talk about when they get past the headlines. And it brings us to one of the most fascinating and genuinely underappreciated aspects of the whole terraforming conversation: the role of life itself. We tend to think of terraforming as something machines do: giant atmospheric processors, orbital mirrors, nuclear-powered heating systems, and those things are all part of the picture. But Earth's own transformation into the world we know was not an engineering project, it was a biological one, and the timeline and the mechanism of that transformation holds lessons that are directly relevant to Mars. About 2.5 billion years ago, Earth's atmosphere contained almost no free oxygen. The planet was dominated by microbes, bacteria and archaea that lived without it, in an atmosphere rich in methane, carbon dioxide and nitrogen. Then something happened that geologists call the Great Oxidation Event. Cyanobacteria, tiny, single-celled photosynthetic organisms, began releasing oxygen as a byproduct of their metabolism. Over hundreds of millions of years, oxygen accumulated. It dissolved in the oceans, it reacted with iron in the seawater, creating the banded iron formations we mine today. Eventually, it built up in the atmosphere to levels that were toxic to most existing life, causing what some scientists call the first mass extinction. But that also opened the door to the explosion of complex, oxygen-breathing life that followed. Earth terraformed itself. Biology did what no machine could have done. It patiently, persistently, at microscopic scale, rebuilt the chemistry of an entire planet's atmosphere over geological time. Could biology do the same thing on Mars? This is the field of planetary bioengineering, and it is where some of the most exciting and most contested science is happening right now. The basic idea is to use genetically engineered microorganisms as the biological engine of atmospheric transformation. Not Earth microbes dropped onto Mars unchanged. Martian conditions would kill most of them almost instantly, but microbes that have been carefully redesigned using synthetic biology tools to tolerate the cold, the radiation, the perchlorates, the desiccation, and the low pressure of the Martian environment. The field of synthetic biology has advanced dramatically in the past 2 decades. CRISPR gene editing, the tool developed by Jennifer Doudna and Emmanuelle Charpentier, who won the Nobel Prize in Chemistry in 2020, has made it possible to edit genomes with a precision and speed that was unimaginable a generation ago. Scientists are already engineering microbes to perform specific industrial tasks on Earth, producing biofuels, breaking down plastics, synthesizing medicines. The question being seriously explored now is whether similar approaches could produce organisms capable of surviving and functioning on Mars. Research groups have already been working on this. A 2019 study by researchers at the University of Rome, published in the journal Astrobiology, investigated which existing extremophile organisms, creatures that survive in the most hostile environments on Earth, show the greatest tolerance for Mars-like conditions. The candidates include certain strains of cyanobacteria that can survive ultraviolet radiation, extreme desiccation, and freezing temperatures. They include methanogenic archaea, microbes that produce methane as a metabolic byproduct, which could theoretically contribute to greenhouse warming. They include perchlorate-reducing bacteria that could potentially detoxify the Martian soil, making it more amenable to other organisms. None of these organisms are ready for Mars. None of them are even close. The gap between Serviv's Mars-like conditions in a lab and Serviv's actual Mars is enormous. The radiationed environment on the surface, with no magnetic field and almost no atmospheric shielding, delivers a radiation dose roughly 40 times higher than what humans experience on Earth's surface. The UV flux is brutal. The temperature swings between day and night can exceed 50 degrees Celsius in a matter of hours, and the perchlorates in the soil, while manageable for some specialized organisms, are toxic to most biology we know of. But the research is not theoretical hand-waving, it is real laboratory science, building toward a real question: what is the minimum viable organism that could establish itself on Mars and begin doing useful chemical work? And how far would we have to push synthetic biology to get there? The answer right now is, we do not know yet, but the direction of travel in the science is clear. The tools are getting sharper. The understanding of extremophile biology is deepening, and the possibility that engineered microbes could serve as the first wave of Martian colonists, not human colonists, but biological ones, is something that planetary scientists are taking seriously in a way they were not even 20 years ago. There is another biological angle to this story that tends to get overlooked entirely. And it is not about what we send to Mars. It is about what Mars might do to us. The human body was not designed for Mars. We evolved on Earth under specific conditions of gravity, radiation, atmospheric pressure, and temperature that shaped every system in our bodies over millions of years. The skeleton, the cardiovascular system, the immune system, the nervous system, all of it is calibrated for one specific planet. Put it somewhere else, and things start to break down. We touched on gravity earlier, the bone density loss, the muscle deterioration, the vision changes. But the radiation problem on Mars is in some ways even more urgent, because unlike gravity, we cannot compensate for radiation just by exercising more. The galactic cosmic rays and solar energetic particles that bombard the Martian surface are deeply penetrating. They go through most materials. They damage DNA. Long-term exposure increases cancer risk significantly and may also have neurological effects. A 2018 study by Charles Limmerle's research group at the University of California, Irvine, published in Scientific Reports, showed that astronauts exposed to simulated cosmic radiation in lab conditions showed cognitive impairment, anxiety-like behavior, and damage to neural structures. These were not trivial effects. They were significant and measurable. So there is a version of the Mars question that turns it completely around. Instead of asking, how do we change Mars to suit humans, it asks, how do we change humans to suit Mars? This is the domain of human genetic engineering and biological augmentation, and it is one of the most ethically fraught conversations in all of science. But it is being had. Seriously, by bioethicists, by geneticists, by futurists at institutions like Oxford's Future of Humanity Institute and MIT's Media Lab. The idea, sometimes called directed human evolution in the context of space colonization, is that over generations, humans living on Mars might be deliberately modified or might naturally select for traits that improve survival in Martian conditions. Denser bones, more efficient oxygen metabolism, greater radiation tolerance. Eventually, after enough generations, you might have something that is still recognizably human, but differently human, a Martian human, shaped by a different world, just as we were shaped by ours. The philosopher and bioethicist Julian Savulescu at Oxford has argued that if we are serious about becoming a multiplanetary species, we need to have an honest conversation about whether that means accepting some degree of modification to our biology. Not because we want to, necessarily, but because the alternative, keeping human biology rigidly fixed while trying to reshape an entire planet, may simply be too slow, too expensive, and too uncertain. This is genuinely uncomfortable territory. The history of human experimentation, of eugenics, of involuntary modification, it casts a long shadow over any conversation about designing human biology. The ethical guardrails here are not optional, they are essential. Any path toward biological adaptation for space would need to be built on consent, on safety, on deep ethical scrutiny. But the fact that the conversation is happening at all, in peer-reviewed journals, in philosophy departments, in the halls of serious institutions, reflects just how seriously some thinkers are taking the challenge of Mars. And underneath all of this, the engineering, the biology, the ethics, the timelines, there is a question that does not get asked enough, one that gets to the heart of why any of this matters at all. Not can we terraform Mars, not how would we do it, but why are we even drawn to this idea? What is it about the human mind that looks at a frozen, irradiated, airless desert 228 million kilometers away and says, we should go there, we should make it home? Part of the answer is survival. The argument made by Stephen Hawking, by Carl Sagan, by Elon Musk, and by many others, a single planet species is a fragile species, an asteroid, a pandemic, a nuclear war, a climate catastrophe. Any of these things could, in principle, end human civilization as we know it. Spreading to another planet is the ultimate insurance policy, not just for us, but for everything we have created, every piece of music, every scientific discovery, every painting, every story that makes us what we are. But there is another part of the answer that is harder to articulate, and perhaps more fundamentally true. We go because we are curious, because we have always moved toward the horizon, whatever it happened to be. Because something in the human brain, something deep, ancient, and probably adaptive, finds irresistible the thing that lies just beyond what we can currently reach. We crossed oceans in wooden boats, not because we were certain of what we would find. We went because not knowing was worse than the risk of going. Terraforming Mars is the longest horizon we have ever seriously contemplated. A project measured not in years or decades, but in centuries, in millennia, possibly in the entire remainder of human civilization. It is an act of radical hope, a commitment made not just to ourselves, but to every generation that will come after us, on a world that does not yet exist, but that we dare to imagine. And right now, in laboratories and control rooms and university research groups, real people are doing real work that points toward that world, not building it, not yet, but understanding it, mapping it, asking the right questions, sending robots ahead of us to test the ground. Speaking of which, because we have been talking a lot about theory, about timelines, about proposals and papers, let us get specific. Let us talk about what is actually happening on Mars right now, today, with the missions currently operating on the surface. Because what those missions are learning, and one discovery in particular that came from the Perseverance rover in 2021, has direct implications for the terraforming question in a way that most coverage completely failed to explain. If you are enjoying this journey, make sure to give this video a like and subscribe to the channel. Every video here is built around real missions, real data, and real wonder. On the 18th of February 2021, a car-sized rover named Perseverance screamed through the Martian atmosphere at roughly 19,000 kilometers per hour and landed in Jezero crater, an ancient lake bed chosen specifically because it showed signs of having once held liquid water, possibly for millions of years. The entry, descent, and landing sequence took 7 minutes. 7 minutes during which NASA's mission control could do absolutely nothing but wait, because the signal delay between Earth and Mars at that point was over 11 minutes each way. By the time they knew the rover had hit the atmosphere, it had already landed, or crashed. Those 7 minutes have been called 7 minutes of terror by NASA engineers, and the nickname is completely earned. Perseverance landed perfectly, and over the following months, it began doing science that will be studied for decades, drilling rock cores from ancient sedimentary formations, deploying the Ingenuity helicopter, a small, lightweight rotorcraft that became the first powered aircraft to fly on another planet, completing its maiden flight on the 19th of April 2021, a moment that echoes the Wright brothers at Kitty Hawk in a way that is genuinely hard to overstate, scanning for biosignatures, chemical and structural traces that might indicate past life in rocks that formed billions of years ago when Jezero was a living, water-filled lake, All of that is extraordinary. All of that matters. But the experiment that matters most for the terraforming conversation, the one that received far less coverage than it deserved, was a small, toaster-sized instrument mounted on the rover's front. It was called MOXIE, which stands for Mars Oxygen In Situ Resource Utilization Experiment. And what it did quietly and efficiently was make oxygen out of the Martian atmosphere. Not oxygen brought from Earth, not oxygen stored in a tank. Oxygen manufactured on the spot from the carbon dioxide that makes up 95% of the air on Mars. The process MOXIE uses is called solid oxide electrolysis. Carbon dioxide molecules, each made of one carbon atom and two oxygen atoms, are drawn in from the Martian atmosphere, heated to approximately 800 degrees Celsius, and pass through a specialized ceramic material called a solid oxide electrolyzer. The electrolyzer splits the carbon dioxide molecules apart, pulling the oxygen atoms free and releasing them as molecular oxygen, the same breathable gas we depend on every moment of our lives. The leftover carbon monoxide is vented back out. In its first operational run on the 20th of April 2021, the same day as Ingenuity's first flight, a remarkable double achievement, MOXIE produced about 5.4 grams of oxygen in an hour. That is roughly the amount a person breathes in about 10 minutes. Not a lot, but that was never the point. MOXIE was a proof of concept, a technology demonstration. What it proved was that the principle works on actual Mars, under actual Martian conditions, with actual Martian atmosphere, not in a simulation. Not in a lab on Earth approximating what Mars might be like. On Mars itself, over subsequent runs through 2021, 2022, and into 2023, MOXIE continued operating and experimenting with different modes of production. A paper published in the journal Science Advances in August 2023 reported that MOXIE had successfully produced oxygen at a rate of up to 10 grams per hour, nearly double its initial output, and had demonstrated consistent performance across a range of Martian seasons and atmospheric conditions. The authors noted that a scaled-up version of the MOXIE system, one roughly the size of a small car rather than a toaster, could potentially produce enough oxygen to sustain a small human crew and provide propellant for a Mars ascent vehicle. Let that sit for a second. A scaled-up oxygen factory, built from technology that already works, fed entirely by the Martian atmosphere, producing the two things humans on Mars need most: air to breathe and fuel to get home. This is not theoretical. The foundation technology has been validated on the actual planet. For the terraforming picture, MOXIE matters in a specific way. It demonstrates that in situ resource utilization, the technical term for using what you find where you are, rather than bringing everything from home, is a real, achievable strategy on Mars. And in situ resource utilization is absolutely central to any serious terraforming plan. You cannot import an atmosphere from Earth. You cannot ship enough greenhouse gas across interplanetary space to warm a planet. Everything has to come from Mars itself, processed by systems operating on Mars. MOXIE is the tiniest possible first step in that direction, but it is a real step. The Perseverance rover has also been doing something else that connects directly to the terraforming story, something that has received almost no mainstream coverage at all. It has been systematically collecting and caching rock samples, drilling cores from the most scientifically interesting formations it encounters, sealing them in small titanium tubes, and depositing them on the Martian surface at carefully recorded locations. As of mid-2024, Perseverance had deposited a cache of 10 sample tubes on the floor of Jezero crater, a location designated as the Three Forks Sample Depot. There are additional samples stored on the rover itself. These samples are intended to be retrieved. The Mars Sample Return Mission, A joint program between NASA and the European Space Agency was designed to send a lander to Mars, deploy a small fetch rover to collect the cached tubes, launch them into Martian orbit aboard a small rocket called the Mars Ascent Vehicle, and then rendezvous with an Earth return orbiter to bring the samples home. If successful, it would be the first time material from Mars had been returned to Earth, since Mars ejected it naturally through ancient impacts, which is how Martian meteorites end up here. However, and this is important to acknowledge honestly, the Mars Sample Return Program has run into serious difficulties. In 2023 and 2024, independent review boards assessed the program and found that its costs had ballooned dramatically, with estimates rising to somewhere between 8 and 11 billion US dollars. NASA's budget constraints meant the program was paused and restructured. As of the knowledge available through early 2025, the future of Mars sample return in its original form was uncertain, with NASA soliciting alternative mission architectures that might achieve the same science goals at lower cost. This matters enormously, because those cached samples contain potentially the most scientifically valuable material humanity has ever assembled. Ancient Martian rock from what was once a lakebed, possibly preserving chemical or even structural evidence of past life. The ability to study that material in Earth laboratories, with the full arsenal of analytical tools that cannot be miniaturized into a rover, could fundamentally transform our understanding of Mars, of its history, of its potential for life, and by extension, of whether terraforming it would be ethically defensible. If we bring those samples home and find absolutely no biosignatures whatsoever, no amino acids in unexpected configurations, no microbial fossils, no isotopic ratios that suggest biological processing, that silence would itself be meaningful. It would push the probability of present or past Martian life downward and make the ethical case for terraforming somewhat easier to argue. Conversely, if the samples contain something, anything, that suggests biology once operated in Jezero crater, the terraforming conversation becomes profoundly more complicated. We genuinely do not know which way that will go, and that uncertainty is not a failure of science. It is science doing exactly what it is supposed to do, withholding conclusions until the evidence supports them. While Perseverance has been doing its work in Jezero, the other active rover on Mars, Curiosity, now well into its second decade of operation in Gale Crater, has continued producing results that reshape our understanding of ancient Mars. In 2023, Curiosity detected the highest concentrations of organic molecules ever found on Mars, carbon-containing compounds preserved in 3.5 billion-year-old mudstones. Organic molecules are not direct evidence of life. They can form through purely chemical, non-biological processes. But they are the building blocks of life as we know it, and their preservation over billions of years in Martian rock is remarkable. It suggests that if life ever did exist on Mars, the chemical ingredients were available. The conditions, at some point in deep time, were right. Gale Crater itself tells a story that planetary scientists find almost poignant. The crater formed about 3.8 billion years ago. For perhaps the first billion years of its existence, it held a lake. Water flowed in from surrounding highlands, deposited sediment, and created the layered geological record that Mount Sharp, the 5.5-kilometer peak rising from the crater's center, preserves like pages in a book. Curiosity has been driving up through those layers, reading the chemical history of that ancient lake, and the story it tells is of a world that was once genuinely wet, genuinely warm, genuinely, at least potentially, habitable. Mars was not always Mars as we know it. It had a different chapter, a warmer, wetter chapter that lasted hundreds of millions of years before the magnetic field collapsed, the atmosphere thinned, and the surface froze. And that earlier chapter is, in a profound way, what makes terraforming feel like something other than pure fantasy, because it means Mars was not always inhospitable. It means the planet has a kind of memory of being more like Earth, a memory locked in its rocks and its minerals and its ancient chemistry. Terraforming would not be creating something entirely new on Mars. In a sense, it would be attempting to restore something very old. There is a phrase that planetary scientists sometimes use, quietly, among themselves. They call it making Mars remember. It is not an official scientific term. It is something more like a shared intuition, the sense that the goal of terraforming is not to impose an alien environment on a foreign world, but to coax a world back toward a condition it once naturally occupied. Whether that framing is literally accurate is debatable. Ancient Mars was not identical to Earth, and any terraformed Mars would be different from both, but the spirit of it captures something real. Mars was not always the enemy of life. Once it may have been its friend. Now all of this, the Moxie experiment, the rock samples, the organic molecules, the ancient lake beds, represents what we are learning right now with robots, with remote sensing, with instruments that can drill a few centimeters into rock and analyze what they find, but cannot dig kilometers into the subsurface, cannot examine the diversity of environments across a planet-sized world, cannot adapt and improvise the way a human scientist in the field can. The next step, the one that changes everything about our ability to understand and eventually act on Mars, is humans. And sending humans to Mars raises a set of challenges that go far beyond the technological, the physiological, the psychological, the logistical. All of it converges into what would be the most complex and dangerous human expedition ever attempted. The journey alone is daunting, depending on the orbital alignment of Earth and Mars, which only achieves its closest approach every roughly 26 months, during what is called a synodic period. A one-way trip to Mars using current or near-future propulsion technology would take somewhere between 6 and 9 months, 6 to 9 months in a spacecraft, in microgravity or near microgravity, bombarded by cosmic radiation with no planetary magnetic field to help, in an enclosed environment with a small crew, with no possibility of emergency evacuation if something goes wrong. The psychological dimension of that journey is something NASA has studied extensively using analog missions, situations on Earth, designed to simulate the isolation and confinement of deep space travel. The Arch-I-CIAS program in Hawaii placed crews in a dome on a volcanic landscape for months at a time, studying group dynamics, communication delays, and psychological resilience. The findings were nuanced. Crews can function, people can manage the isolation, but interpersonal conflict, motivation fluctuation, and what researchers call third-quarter phenomenon, a dip in morale and performance around 3/4 of the way through a long isolated mission, are real and consistent patterns. And once a crew arrives at Mars, they cannot simply turn around and come home if things go wrong. The return window, the orbital alignment that makes the return trip fuel efficient, only opens every 26 months. If an emergency occurs outside that window, the crew either waits or burns enormous amounts of propellant on a non-optimal trajectory. This is not like the Apollo missions, where a damaged spacecraft could loop around the moon and come home in a few days. Mars is a one-way commitment in the sense that you go, you stay for a significant period, and then you come back when the planets allow. These realities, the radiation, the psychology, the orbital mechanics, the sheer distance, are not reasons not to go. They are the shape of the challenge. And understanding the shape of a challenge is the first step to meeting it. Engineers at NASA, at SpaceX, at the European Space Agency, and at a growing number of private companies are working on all of these problems simultaneously. Radiation shielding, closed-loop life support, mental health protocols for long-duration spaceflight. advanced propulsion systems that could reduce transit time from 9 months to perhaps 3 or 4 months, dramatically cutting radiation exposure and the psychological burden of the journey. Nuclear thermal propulsion, an approach that uses a nuclear reactor to heat propellant and expel it at much higher velocities than chemical rockets, has been seriously studied since the 1960s and recently revived as a credible near-term technology. NASA's Draco program, the demonstration rocket for agile cislunar operations, is developing a nuclear thermal rocket demonstrator, with flight tests potentially occurring in the mid-2020s. If nuclear thermal propulsion proves out, it could cut Mars transit time significantly, and faster transit means less radiation exposure, less psychological strain, and a more survivable mission. The convergence of all these threads, better propulsion, validated in situ resource utilization, growing understanding of Martian geology and potential biology, improving synthetic biology tools, serious proposals for magnetic shielding, does not make terraforming Mars easy. It does not make it imminent, but it does make it look, increasingly, like something that belongs in the category of genuinely possible rather than pure speculation. And there is one more thread to pull, one that connects the very largest scales of this story to the very smallest. One that brings us back to the idea that we are not just talking about engineering when we talk about terraforming Mars. We are talking about something that touches the deepest questions of what life is, where it comes from, and what the universe might be doing when it produces creatures like us, who look back at it and ask these questions. That thread is panspermia, and the evidence for it and what it implies for Mars is genuinely startling. Here is something that will quietly rearrange the furniture in your mind. In 1984, a group of meteorite hunters working on the Allen Hills ice field in Antarctica found a rock. It was not remarkable looking, roughly the size of a potato, greenish-grey, sitting on the ice where the wind had swept the surface clean. They catalogued it as ALH 84001 and shipped it to the Johnson Space Center in Houston, where it sat in storage for nearly a decade before anyone looked at it closely enough to realize what it was. It was a piece of Mars. Ejected from the Martian surface roughly 16 million years ago by a massive asteroid impact, it had drifted through interplanetary space before being captured by Earth's gravity and falling to Antarctica approximately 13,000 years ago. When scientists finally analyzed it in depth in the mid-1990s, they found something that caused one of the most extraordinary press conferences in the history of science. On the 9th of August, 1996, NASA Administrator Daniel Goldin stood at a podium and announced that the research team studying ALH 84001 had found potential evidence of ancient Martian life inside the rock. Carbonate globules, polycyclic aromatic hydrocarbons, magnetite crystals of a type produced on Earth almost exclusively by bacteria, and most controversially, microscopic structures that looked, under electron microscopy, like fossilized nanobacteria. President Bill Clinton made a statement from the White House lawn. The world held its breath, and then the scientific community did what it is supposed to do. It scrutinized, it challenged, it argued. Over the following years, alternative explanations emerged for every feature the team had identified. The magnetite crystals could form through non-biological heating. The organic compounds could be contamination from Earth. The microstructures were too small, smaller than any known cell, to plausibly house the biochemical machinery life requires. The consensus that emerged, gradually and not without dissent, was that the evidence was intriguing but not conclusive, not proof of life. A question mark, not an answer. But here is what that debate obscured, what got lost in the noise of the controversy. The fact that pieces of Mars regularly arrive on Earth is not in dispute, it is confirmed. We have identified over 300 Martian meteorites in collections around the world as of the mid-2020s, and the mechanism that sends them here, a large impact on Mars ejecting surface material at escape velocity, also works in reverse. Large impacts on Earth over the 4.5 billion year history of our solar system have certainly ejected material from our planet into space. Some of that material, carrying whatever was living in it at the time, would have followed trajectories that eventually intersected Mars. This is the core of the panspermia hypothesis as it applies to our solar system. Not that life necessarily travels between the stars, that is a much harder case to make, but that within a single solar system, between neighboring planets, the exchange of material is real, documented, and has been happening for billions of years. The question is not whether rocks travel between Earth and Mars. They do. The question is whether anything living could survive the journey. And this is where the science gets genuinely surprising, because the answer, based on real experimental evidence, is possibly yes. Tardigrades, microscopic animals sometimes called water bears, roughly 0.5 millimeter long, are arguably the most radiation-resistant, complex organisms known to science. They can survive temperatures from near absolute zero to over 150 degrees Celsius. They can withstand pressures 6 times greater than the deepest ocean trench. They can be completely desiccated, every molecule of water removed from their bodies, and remain viable for decades, reviving when water is reintroduced, and they can survive radiation doses that would kill a human thousands of times over by producing a unique protein called DSUP, damage suppressor, that physically shields their DNA from radiation damage. Research published in 2019 by Thomas Boothby's group at the University of Wyoming showed that the DSUP protein, when transferred into human cells in laboratory conditions, reduced radiation-induced DNA damage by around 40%. The biology that keeps tardigrades alive in space-like conditions is real, measurable, and transferable. These are not fairy tales about tough little animals. They are documented molecular mechanisms that evolution produced on Earth. Bacterial spores, particularly those of the genus Bacillus, have been tested extensively for survivability in simulated space conditions. Experiments aboard the European Space Agency's Expose platform, mounted on the outside of the International Space Station and exposed directly to the vacuum and radiation of space for up to 3 years, have shown that certain bacterial spores can survive that exposure, particularly when shielded by even a thin layer of rock. The rock provides enough protection from the most damaging ultraviolet radiation to allow survival over timescales consistent with interplanetary transfer. What this means, taken together, is that panspermia within our solar system is not physically forbidden. It is not even particularly unlikely, given the billions of years over which it could have operated. Life that originated on Earth could in principle have reached Mars. Life that originated on Mars, if it ever existed, could in principle have reached Earth. We might, in a very real sense, be Martians. The atoms in your body were forged in dying stars. That much is certain. But the first living cells whose descendants eventually became you, we genuinely do not know where the spark of life first ignited in this solar system. This possibility, quiet, strange, humbling, has direct implications for the terraforming debate. Because if life did travel between Earth and Mars at some point in the deep past, it complicates the ethical picture considerably. It means Mars and Earth may share a biological heritage. It means that life, if it exists in the Martian subsurface today, might be our distant cousin rather than a truly alien form of biology. And it means that introducing Earth organisms to Mars as part of a biological terraforming program might not be the radical contamination it first appears. It might be, in a strange way, a kind of return, or it might not. Because the other possibility, that life arose independently on Mars, following a completely different biochemical pathway built from different molecular machinery, is also real. If that is the case, then Martian life would be the most scientifically precious thing in the known universe, more valuable than any mineral deposit, any geological formation, any piece of ancient rock. It would tell us that life is not a fluke, that given the right conditions, chemistry tends toward biology, that the universe is in some deep sense biologically inclined, that we are not alone, not even in our own solar system. Finding that, and then overwriting it with engineered microbes because we wanted a warmer planet, would be an act of destruction without precedent, an irreversible loss. The kind of thing that future generations looking back might regard with the same horror we feel when we contemplate the extinction of species or the destruction of irreplaceable cultural heritage. This is why the question of Martian life, even microbial, even hypothetical, even buried kilometers underground, is not a side issue in the terraforming conversation. It is the central ethical issue. Everything else, the engineering, the biology, the timescales, the cost, is secondary to this. And yet it is the question that gets the least attention in popular coverage of Mars exploration, because microscopic underground bacteria are harder to make exciting than rockets and domes, and the image of humans walking on another world. Let us talk about what we actually know about the possibility of present-day life on Mars, not ancient life, but life that might be alive right now, because the picture here is more nuanced than most people realize. The surface of Mars, as we have established, is deeply hostile. Radiation perchlorates, extreme cold, almost no liquid water. Life on the surface exposed is almost certainly impossible. But the surface is not the whole story. Mars has a subsurface. It has ancient hydrothermal systems, networks of cracks and conduits where volcanic heat once drove water through rock, creating exactly the kind of warm, chemically rich environment where life thrives in the deep ocean floors of Earth. We know these systems existed because we can see their mineralogical signatures from orbit, clay minerals, sulfates, carbonates that form in the presence of liquid water and heat. Some of these hydrothermal systems may still be active. Mars is not entirely geologically dead. Marsquakes detected by NASA's InSight lander, which operated on the Martian surface from November 2018 until December 2022, when dust accumulation on its solar panels ended the mission, confirmed that Mars has ongoing seismic activity. The planet is not a cold, inert ball of rock. It still has internal processes. Whether those processes generate enough heat to maintain liquid water in localized subsurface environments, the kind where microbial life could persist, is genuinely unknown. InSight's contribution to this story is worth pausing on. It was the first mission dedicated to studying the deep interior of Mars, using a seismometer sensitive enough to detect Marsquakes smaller than magnitude 1 and a heat flow probe designed to burrow 5 meters into the Martian soil to measure how much heat the planet radiates from its interior. The heat flow probe, unfortunately, encountered unexpectedly hard soil and was unable to reach its target depth, one of the mission's significant frustrations. But the seismometer worked beautifully, detecting over 1,300 Marsquakes over the course of the mission, including several significant events exceeding magnitude 5. The seismic data has allowed scientists to build the first detailed model of Mars's interior structure, its crust thickness, its mantle properties, its core size and composition. The core, it turns out, is larger and less dense than expected, suggesting it is liquid and contains significant amounts of lighter elements like hydrogen, oxygen, sulfur and carbon, in addition to iron and nickel. A liquid core is significant. It means Mars still has some of the internal dynamics that in Earth's case drive the magnetic field. The reason Mars's liquid core does not generate a magnetic field The way Earth's does is almost certainly related to differences in convection, the churning motion within the liquid metal that drives the dynamo effect. On Earth, convection in the outer core is vigorous. On Mars, it appears to be sluggish or absent, but a liquid core is still a liquid core. And understanding it precisely, as InSight's data is now allowing, is essential for any long-term thinking about Mars's evolution and future. The picture that emerges from all of these missions, Curiosity, Perseverance, InSight, Marvin, Mars Express, Mars Reconnaissance Orbiter, is of a world that is far more complex, far more dynamic, and far more surprising than the simple dead red desert image suggests. Mars has hidden water, Mars has ongoing seismic activity, Mars has organic chemistry preserved in ancient rocks, Mars has a liquid core, Mars has weather systems, dust storms that can grow to envelop the entire planet, lasting for months, as happened in 2018, when a global dust storm ended the Opportunity rover's 15-year mission by blocking the sunlight it needed for power. Each of these facts matters for terraforming in specific ways. The hidden water matters for the resource inventory. The seismic activity matters for understanding geological risk to any surface infrastructure. The organic chemistry matters for the biosignature search and the ethical question. The liquid core matters for understanding whether Mars might, under the right circumstances, reactivate any magnetic field, or whether an artificial one truly is the only option, and those dust storms matter in a way that is easy to underestimate. A global dust storm on Mars lasts months. During that time, solar panels generate almost no power, which is what killed Opportunity. Any long-term human presence on Mars, let alone any terraforming infrastructure, would need to be hardened against these events. Nuclear power sources, like the radioisotope thermoelectric generators that power Curiosity and Perseverance's instruments, are immune to dust storms. But scaling nuclear power to the levels needed for serious terraforming infrastructure is a challenge of its own. Here is a number worth sitting with. The total power consumption of human civilization on Earth right now is approximately 18 terawatts, 18 trillion watts. That is everything, every factory, every city, every vehicle, every device, every light bulb on the planet. Some estimates of the energy required to terraform Mars, to manufacture synthetic greenhouse gases at scale, to power atmospheric processors, to run whatever magnetic shield system might be deployed, run into figures comparable to Earth's total current energy budget, not slightly less, comparable. Some estimates go higher. Where does that energy come from on Mars? Solar power is less effective there because of the distance from the sun and the dust storms. Wind power is theoretically possible. Mars does have wind, but the thin atmosphere means wind carries very little energy compared to Earth. Nuclear power is the most credible answer for the near term, but the scale of nuclear infrastructure required for a full terraforming program is staggering. Thousands of large reactors built on another planet from materials sourced wherever they can be found. This is why some researchers have proposed a different energy source entirely, one that is not limited by planetary resources or solar distance, one that, if it can be made to work, would change everything, not just for Mars but for human civilization as a whole. Fusion power. Controlled nuclear fusion, the same process that powers the sun, has been the perpetual 30 years away promise of energy research for the past 7 decades. But in December 2022, the National Ignition Facility at Lawrence Livermore National Laboratory in California achieved something historic, a fusion reaction that produced more energy than the lasers used to initiate it. For the first time in history, a fusion experiment achieved what scientists call ignition, the point at which the fusion reaction becomes self-sustaining rather than requiring a continuous energy input. The energy gain was modest, about 3.15 megajoules out from 2.05 megajoules in, but the principle was proven. Fusion ignition is real, it works. That does not mean commercial fusion power is around the corner. The path from a laboratory demonstration to a working power plant is long and complex, involving engineering challenges that are distinct from the physics challenges. But the direction of travel is clear. Private fusion companies, Commonwealth Fusion Systems, Helion Energy, TAE Technologies, and others are attracting serious investment and making measurable technical progress. The timeline for practical fusion power remains uncertain, but it is no longer credibly described as impossible. And if fusion power becomes practical within this century, which some researchers now consider plausible, it would provide essentially limitless energy from hydrogen isotopes that are abundant throughout the solar system, including on Mars. A fusion-powered terraforming program would look radically different from one limited to fission reactors and solar panels. The energy constraint, the single most fundamental physical limitation on how fast Mars could be transformed, would effectively dissolve. This is why the terraforming conversation cannot be had in isolation from the broader trajectory of human technology. The feasibility of terraforming Mars depends not just on what we know today, but on what we will know and be able to do in 50, 100, 500 years. And if the history of science teaches us anything, it is that the pace of discovery and technological development consistently surprises even the optimists. Carl Sagan wrote, in Pale Blue Dot, that the Earth is a very small stage in a vast cosmic arena. He was pointing toward humility, toward the recognition that our planet, seen from far enough away, is a pale blue dot against the blackness of space, fragile, precious, alone, as far as we can see, in a universe of almost incomprehensible scale. But there is another reading of that image. The famous photograph taken by Voyager 1 on the 14th of February 1990, from a distance of about 6 billion kilometers. In that reading, the pale blue dot is not just a reminder of fragility, it is a reminder of possibility. Because whatever made that dot blue, whatever combination of liquid water and living organisms and atmospheric chemistry turned a rock into a world, is not magic. It is physics and chemistry and biology operating under conditions that, while rare, are not unique to Earth. Mars could be blue again, not the same blue, not the same world, but something alive, something breathing, something that future generations might look at from their own pale dot and feel the same awe that we feel when we look at Earth from space. Whether that future is possible, and what the next concrete steps toward it actually look like, beyond the missions and the proposals and the theoretical frameworks we have explored, is what we need to examine next. Because there is a roadmap. It is incomplete, it is contested, but it exists. And the people working on it are not dreamers. They are scientists and engineers doing methodical, careful, real work. Every great undertaking in human history has had a moment where it stopped being a conversation and became a construction site, where the blueprints came off the wall and the first physical thing was built. For the Apollo program, that moment was arguably the groundbreaking of the Vehicle Assembly Building at Cape Canaveral in 1963, the largest building by volume ever constructed at the time, built specifically to house the Saturn V rocket that would take humans to the Moon. For the International Space Station, it was the launch of the Zarya module in November 1998, a single pressurized cylinder, barely habitable, the first piece of what would become a permanently crewed outpost in low Earth orbit. For the Channel Tunnel, it was the moment two boring machines, one started from England and one from France, finally broke through to meet each other beneath the seabed in December 1990. Every impossible project has a moment where it becomes real. For Mars, we have not had that moment yet, but we are closer to it than most people realize. And understanding what that first real moment might look like what the first genuinely irreversible step toward a human Mars civilization would be, requires understanding the roadmap that serious mission planners, planetary scientists, and space agencies are actually working from. That roadmap does not begin with terraforming. It cannot. Terraforming is the last chapter of a story whose first chapters are about something more fundamental: survival. Before you can transform a planet, you have to be able to stay alive on it long enough to do the work. And staying alive on Mars for humans requires solving problems that are simultaneously deeply practical and genuinely novel. Let us walk through what a realistic first century of human engagement with Mars might actually look like. Not the optimistic version, not the pessimistic version, but the version that emerges when you take the current state of technology, the known challenges, and the historical pace of development seriously. The first phase, call it the reconnaissance and infrastructure phase, is already underway. This is the era of robotic missions, rovers, landers, orbiters, building the detailed knowledge base that human missions will eventually depend on, mapping the subsurface with ground-penetrating radar, identifying the most accessible water ice deposits, characterizing radiation environments at potential landing sites, testing technologies like MOXIE that will be needed at scale. We are deep inside this phase right now, and it will continue for at least another decade, probably two. Within this phase, there are specific milestones that matter enormously for what comes next. One of them is the identification of lava tubes. Mars, like the Moon, almost certainly has lava tubes, underground tunnels formed when the outer crust of a lava flow solidified while molten rock continued flowing beneath, eventually draining and leaving a hollow tube behind. On Earth, lava tubes can be a few meters across. On the Moon, orbital radar data suggests some lava tubes may be hundreds of meters in diameter. On Mars, because of the lower gravity, which allows volcanic structures to be larger before they collapse, some researchers have estimated that Martian lava tubes could be kilometers wide and tens of kilometers long. Enormous underground caverns, naturally shielded from radiation by meters of rock overhead, potentially maintaining more stable temperatures than the surface, and possibly trapping enough atmospheric gas inside to maintain slightly higher pressure than the open surface. If large lava tubes exist on Mars in the sizes some models predict, they represent perhaps the single most valuable real estate in the solar system for early human habitation. A natural shelter, radiation protection built in, structural integrity provided by billions of years of geological history, the possibility of enclosing them, sealing the entrance, pressurizing the interior, creating a livable volume without building every centimeter of habitat from scratch, is genuinely compelling. The JAXA, Japan Aerospace Exploration Agency, lunar orbiter Kaguya, identified what appeared to be a lava tube entrance pit on the Moon in 2009. More recently, data from the Grail mission confirmed the existence of subsurface void structures consistent with lava tubes beneath the lunar surface. Mars orbiters have identified similar pit structures that may indicate lava tube entrances. Future missions specifically designed to probe these structures with ground-penetrating radar, potentially including dedicated cave exploration robots, could be among the most consequential planetary science missions of the coming decades. The second phase of the roadmap, the human foothold phase, is where the conversation shifts from robotic to crewed. This is the phase that space agencies and private companies are currently racing toward, with timelines ranging from the optimistic to the wildly optimistic. NASA's current planning, under the Artemis program framework that aims to return humans to the Moon as a stepping stone, has cited the late 2030s as a potential target for initial crewed Mars missions. SpaceX, under Elon Musk's publicly stated ambitions, has repeatedly suggested crewed Mars landings could happen by the late 2020s, though these timelines have consistently slipped. What would a first crewed Mars mission actually look like? The most credible mission architectures, including NASA's Design Reference Architecture 5.0, a detailed engineering study, envision a surface stay of roughly 500 days. Not a quick visit, not a flags and footprints mission like Apollo. 500 days on the surface, using the time productively before the return window opens. A crew of 4 to 6 people, a pre-deployed surface habitat and resource utilization equipment sent ahead on earlier cargo missions, an ascent vehicle fueled using Martian resources, including oxygen produced by a scaled-up MOXIE-type system waiting on the surface before the crew even leaves Earth. That last point is critical. You do not send humans to Mars until you have independently verified that the ascent vehicle is fueled, functional and ready. No vehicle, no crew. That is the rule, because there is no rescue mission. The psychological reality of a 500-day surface stay on Mars deserves more attention than it typically gets. In the HICAS studies we mentioned earlier, the longest continuous analog mission lasted 12 months. Real Mars surface missions would be longer, more isolated, and carrying genuine mortal risk in a way that even the most realistic Earth-based simulation cannot fully replicate. The crew members would know, not hypothetically, but actually, that if something went catastrophically wrong, help was between 3 and 22 light minutes away in terms of communication and months away in terms of physical assistance. That knowledge changes the psychology of the situation in ways that are difficult to model in a Hawaiian lava field. Research on Antarctic overwinter crews, perhaps the closest real-world analog to the isolation and confinement of a Mars surface mission, has identified consistent patterns. The importance of meaningful work in maintaining psychological health, the critical role of interpersonal dynamics within small groups, the value of autonomy and personal space, and the surprisingly significant impact of aesthetic environment on mood and cognitive function. That last point, aesthetics, has led some mission designers to think seriously about things like natural lighting cycles, plant growth, art, and personalized private quarters as non-negotiable mission elements rather than luxuries. A mission that keeps its crew psychologically healthy for 500 days is not a soft goal. It is a survival requirement. The third phase, and this is where the terraforming conversation begins to shift from theory to early practice, is what you might call the permanent settlement phase. This is the point at which the Mars population stops being a rotating crew of visiting scientists and engineers and becomes a community with children born on Mars, with institutions, with an economy, with a culture distinct from Earth's. Some researchers place this transition at a population of roughly 1,000 permanent residents. Others say 10,000. The number is less important than the concept. The moment Mars becomes self-sustaining in terms of human reproduction and knowledge generation, the moment it stops depending entirely on Earth for people and ideas, is the moment the project takes on a different character entirely. Because here is something that does not get discussed enough. A self-sustaining Mars colony would, over generations, inevitably develop its own perspective on Mars, its own relationship with the planet. And that relationship might be very different from the one imagined by the Earth-based engineers and scientists who designed the first missions. People who are born on Mars, who grow up under its sky, who know its seasons and its dust storms and its sunsets. Those people will have opinions about what Mars should become, and those opinions may not align with any terraforming plan drawn up on Earth. The political and social dimensions of a Mars colony are not just sociological curiosities, they are practically important. A terraforming program that takes centuries to complete will span many generations of Martian-born inhabitants who had no say in the decision to begin it. The ethical framework for intergenerational consent, for making decisions that bind people not yet born to a planetary-scale project, does not currently exist. It is one of the genuinely novel ethical problems that a serious commitment to Mars colonization would force humanity to develop. These are not reasons to abandon the project. They are reasons to think about it more carefully, more honestly, and with more humility than the enthusiastic boosterism that tends to dominate public conversations about Mars. Now, let us get specific about the early terraforming steps, because if we assume that humanity does establish a permanent settlement on Mars, and that settlement grows to the point where large-scale planetary engineering becomes a real priority, what do the first actual terraforming actions look like? What do you do first? The scientific consensus, to the extent there is one, points toward warming as the first priority. You cannot do much else until the average temperature rises enough to begin releasing frozen resources and stabilizing liquid water. And the most credible near-term warming strategy is the production of super greenhouse gases. The chemistry here is worth understanding in some detail because it is genuinely fascinating. The most effective greenhouse gases known to science in terms of heat-trapping ability per molecule are not carbon dioxide or methane. They are perfluorocarbons, or PFCs, synthetic compounds made entirely of carbon and fluorine atoms. Compounds like octafluoropropane, hexafluoroethane, and tetrafluoromethane are capable of trapping heat at rates thousands to tens of thousands of times more effectively than carbon dioxide, molecule for molecule. They are also extraordinarily stable, persisting in an atmosphere for thousands of years without breaking down. That persistence, which makes them environmentally disastrous on Earth, makes them exactly what you want for a terraforming project. You want your greenhouse gas to stay in the atmosphere and keep working for a very long time. The key raw materials needed to produce PFCs are carbon and fluorine. Carbon is abundant on Mars, in the atmosphere, in the rocks, in organic compounds preserved in the soil. Fluorine is present in Martian minerals, though extracting it in large quantities presents engineering challenges. A paper by Robert Zubrin and Christopher McKay, published in the journal Advances in Space Research in 1997 and still considered a foundational reference in the field, outlined a detailed scenario for PFC production on Mars, estimating the factory sizes, energy requirements, and production timescales needed to achieve meaningful warming. Their calculations suggested that a network of PFC factories running on nuclear power could raise Mars's average temperature by around 10 degrees Celsius over a period of a few decades, enough to begin significant melting of polar ice and the release of frozen carbon dioxide. 10 degrees Celsius of warming achieved in decades rather than millennia. That is a genuinely significant result. If the assumptions hold, and if the resources are available at the required scale, and if the factories can be built and maintained on a planet where every component has to be manufactured locally or shipped from Earth at enormous cost. Each of those conditional clauses represents a mountain of engineering work. But the mountains are not infinite, they have tops. There is another warming strategy that operates on a completely different scale and has a certain audacious elegance to it: orbital mirrors. The concept involves placing one or more large reflective structures in Martian orbit to redirect additional sunlight onto the surface, particularly onto the polar ice caps, to accelerate their sublimation. The physicist and Mars advocate Christopher McKay, along with colleagues including Robert Zubrin and Margarita Marinova, has written about this approach in detail. The mirrors would need to be enormous. McKay's calculations suggested a single mirror of around 125 kilometers in diameter could raise Mars's average temperature by around 5 degrees Celsius. Constructing something that large in space is far beyond current capability, but it could potentially be built from materials mined on Mars or on nearby asteroids using robotic manufacturing systems. Again, not forbidden by physics, an engineering problem. The combination of PFC production and orbital mirrors represents what some researchers call a fast-track warming scenario, one in which dedicated industrial effort, sustained over decades, produces measurable changes in global Martian temperature within a human lifetime, not terraforming complete, not atmosphere breathable, but warming, measurable real planetary scale warming, initiated by human industrial activity on another world. The thought of that is almost vertiginous, and here is where the biology comes back into the picture. Because as the temperature rises and the atmosphere thickens, even slightly, the range of environments on Mars that could potentially support engineered microbial life begins to expand. The first biological colonists of Mars would not be humans, they would be microbes, hardy, engineered, perchlorate-tolerant, radiation-resistant, methane-producing, oxygen-releasing organisms designed in synthetic biology laboratories on Earth and released into the warming Martian environment to begin the slow, patient work of biological atmospheric engineering. What environments would they target first? The most promising candidates are not the open surface. They are sheltered microenvironments, places where liquid water might briefly exist during the warmest parts of the Martian day, or where subsurface warmth creates a hospitable niche, crater walls facing the equator, subsurface cracks where geothermal heat keeps temperatures above freezing, the underside of translucent rocks, a phenomenon called endolithic habitation, where certain Earth organisms live just beneath the surface of transparent minerals, sheltered from UV radiation while still receiving enough light for photosynthesis. Mars has plenty of translucent minerals. The ecological niche already exists. It just needs occupants that can survive there. The concept of designing an ecological succession for Mars, a planned sequence of organisms, each one modifying the environment in ways that make it more hospitable for the next, is called directed panspermia in some literature and ecological engineering in others. It mirrors deliberately and consciously the way Earth's biosphere evolved from simple chemotrophic microbes to the extraordinary complexity of today's ecosystems. But it would be compressed and directed, driven by human intention rather than random mutation and natural selection, at least initially. Over geological time, whatever biology took hold on Mars would begin evolving on its own, adapting to local conditions in ways no designer could fully predict. Life, once established, tends to find its own way. There is something genuinely moving about this vision, the idea that we could seed another world, carefully, thoughtfully, with full awareness of what we are doing, and then watch as life takes root and begins writing its own story, that the descendants of engineered microbes, evolved beyond recognition over millions of years, might one day be the ancestors of an entire Martian biosphere, that the universe, which spent 13.8 billion years producing the conditions for life on Earth, might, through the deliberate action of one curious, restless, stardust-built species, produce a second living world in this corner of the galaxy. We are, all of us, made of atoms forged in stellar cores. The iron in your blood was made in a dying star, the calcium in your bones, the oxygen you breathe, all of it was processed through stellar interiors over billions of years before a supernova scattered it into space, where it eventually became part of the cloud that collapsed to form our sun and its planets. You are, in the most literal and beautiful sense, a way for the universe to know itself, a way for matter to become curious about its own origins, and if that is what we are, if curiosity is written into us at the level of physics, then the impulse to look at Mars and ask, could something live there, is not just ambition, it is the universe asking a question about itself, through us, using us as its instrument of inquiry. That framing, which comes as much from philosophy and poetry as from science, does not make the engineering easier. It does not solve the magnetic field problem, or build the atmospheric factories, or resolve the ethical questions about Martian life. But it situates the whole enterprise within something larger than any individual mission or any individual human lifetime. It makes the project feel, in the deepest sense, worth doing, not because we are sure we will succeed, but because the asking of the question is itself an act of meaning, and sometimes, in science as in life, the asking of the question is where everything begins. If you are still watching, don't forget to subscribe and give this video a like. You will be part of a community that explores the cosmos together. In 2023, a research team led by Xiaocheng Zheng at the University of Arizona published a study in the Journal of Geophysical Research that quietly shifted the conversation among planetary scientists in a way that has not yet fully penetrated public awareness. What they did was build the most detailed and comprehensive model yet of how a terraformed Martian atmosphere would behave over time, specifically how quickly it would be eroded by the solar wind under different magnetic shielding scenarios. Their findings were sobering in some respects and genuinely encouraging in others. And understanding what they found requires understanding something about the solar wind that most people do not know, something that makes the atmosphere stripping problem both worse and more tractable than it first appears. The solar wind is not constant. It is not a steady, uniform stream of particles blowing outward from the sun at a fixed speed and density. It is dynamic, variable, and punctuated by violent events called coronal mass ejections, enormous eruptions from the solar surface that hurl billions of tons of magnetized plasma into space at speeds of up to 3,000 kilometers per second. When a coronal mass ejection hits Earth, our magnetic field deflects most of it, though the interaction can still cause geomagnetic storms powerful enough to disrupt power grids and satellite communications. The 1989 Quebec blackout, which left 6 million people without power for up to 9 hours, was caused by a geomagnetic storm triggered by a coronal mass ejection. The Carrington event of 1859, the most powerful geomagnetic storm in recorded history, was so intense that auroras were visible as far south as the Caribbean, and telegraph systems across North America and Europe caught fire spontaneously. On Mars, without a magnetic field, coronal mass ejections hit the upper atmosphere directly. Maven measured the effect of a particularly powerful solar storm in March 2015 and found that during the event, atmospheric loss rates spiked to roughly 10 to 20 times their baseline level. A single major coronal mass ejection stripped more atmosphere from Mars in a few days than the steady solar wind removes in months. Over geological time, these episodic stripping events, not just the constant background erosion, are responsible for a significant fraction of the total atmospheric loss Mars has suffered since its magnetic field collapsed. What Zheng's team modeled was how different artificial magnetic field configurations would perform against both the steady solar wind and these episodic events. Their results suggested something important: a magnetic shield positioned at the Mars-Sun L1 Lagrange point, the location proposed by Jim Green's team in 2017, would be most effective against the steady solar wind, but would provide only partial protection against the most intense coronal mass ejections, which can approach from angles that a fixed L1 shield does not fully cover. A more comprehensive protection system might require multiple smaller magnetic field generators distributed around Mars in different orbital positions, working together to create a more complete electromagnetic bubble around the planet. This is more complex and more expensive than the single L1 shield proposal, but it is not fundamentally different in kind. It is the same physics applied at larger scale with greater sophistication, and the modeling suggests that a well-designed multi-node magnetic shielding system could reduce atmospheric loss rates by over 90% compared to the unshielded baseline, enough that any atmosphere built up through terraforming would persist on timescales of millions of years rather than being stripped away within tens of thousands. Millions of years, that is longer than anatomically modern humans have existed. It is longer than any civilization we know of has lasted, and it raises a genuinely profound question. What does it even mean to plan something on that timescale? What kind of institutional commitment? What kind of civilizational continuity? What kind of shared purpose persists across millions of years? The honest answer is, we do not know. We have never sustained a purposeful project across even 10,000 years, let alone a million. The oldest continuously maintained human institution is arguably the Catholic Church, at roughly 2,000 years. The oldest continuously inhabited city is debated, but most candidates fall in the range of 8 to 10,000 years. A terraforming project that requires millions of years of sustained atmospheric protection is in that sense a commitment that transcends any institution, any civilization, perhaps any version of humanity that currently exists. But here is the reframe that changes everything. The magnetic shielding system does not need to be managed by humans for millions of years. It needs to be built once, or maintained at some level of ongoing operation, but the goal is to eventually make it unnecessary. The goal is to restore enough of Mars's own natural protection that the artificial shield can be reduced or removed. And that goal connects to one of the most ambitious and fascinating proposals in all of planetary science, the possibility of reactivating Mars's own core dynamo. This idea, sometimes called core reactivation, is at the outermost edge of what current science can seriously contemplate. The concept is straightforward in principle. Mars's magnetic field collapsed because convection in its liquid iron core slowed and stopped. The question is, could we restart it? Could we somehow inject enough energy into the Martian interior to drive convective motion in the core and regenerate a natural planetary magnetic field? The energy required is staggering. The thermal energy difference between a convecting core and a stagnant one is enormous. We are talking about geological scale heat flows. Some proposals have involved directing asteroid impacts at specific locations to inject kinetic energy into the planetary interior. Others have suggested using arrays of massive electromagnetic coils on the surface to drive currents through the conducting rock of the mantle and indirectly stimulate core motion. None of these ideas are currently anywhere near feasible. The physics is not obviously forbidden, but the engineering gap between where we are and where we would need to be is measured in civilizational timescales, not decades. What is more interesting, perhaps, is what the InSight data has revealed about why Mars's core convection stopped in the first place. The leading hypothesis involves the structure of the Martian mantle, the layer of rock between the crust and the core. On Earth, the mantle convects vigorously, carrying heat from the deep interior to the surface over millions of years and driving plate tectonics. On Mars, the mantle appears to be more viscous, more resistant to flow, possibly because of differences in composition and temperature that developed early in the planet's history. This sluggish mantle insulated the core too effectively, preventing the heat loss that drives convection. In a sense, Mars smothered its own magnetic field by trapping heat rather than releasing it. Understanding this mechanism in detail, which InSight's seismic data is helping to enable, is not just academic. It is the first step toward knowing whether any intervention is theoretically possible. You cannot engineer a solution to a problem you do not fully understand. And our understanding of Mars's interior has advanced more in the past decade than in all the preceding decades of Mars exploration combined. Let us step back from the deep future for a moment and talk about something more immediate, something that is happening right now in the present decade that will shape the entire trajectory of humanity's relationship with Mars, something that has nothing to do with rockets or rovers or magnetic shields, something social, something political, something that, in the long run, may matter more than any single technological breakthrough. We are, right now, in the process of deciding, collectively, without ever having voted on it, without any formal international agreement, largely through the actions of private companies and individual nation-states, what the rules are for going to Mars, who gets to go, what they are allowed to do when they get there, how decisions about planetary-scale interventions will be made and by whom. And we are making these decisions largely by default, in the absence of any coherent global framework. The Outer Space Treaty of 1967, the foundational document of international space law, established some basic principles. Space is the province of all mankind. Nations cannot claim sovereignty over celestial bodies. Nuclear weapons cannot be placed in orbit or on the moon or other bodies, but the treaty was written in the context of the Cold War space race, when space activity was exclusively the domain of nation-states, and the idea of private companies landing on Mars was pure science fiction. It is showing its age badly. The question of planetary protection, the policy framework governing how human missions can interact with potentially life-bearing environments, is managed by an international body called COSPAR, the Committee on Space Research. COSPAR classifies solar system destinations into categories based on their potential for harboring life and sets requirements for how sterile spacecraft must be before visiting them. Mars is classified as a Category 4 destination for missions that might contact water environments, requiring extremely rigorous sterilization of any hardware that could contact potential liquid water habitats. But these are guidelines, advisory frameworks. They have no enforcement mechanism. They depend on the goodwill and self-regulation of the mission's operators. When private companies, not bound by the same international obligations as national space agencies and driven by commercial incentives, begin landing on Mars, the adequacy of this framework will be tested severely, and the stakes could not be higher. Contaminating Mars with Earth organisms before we have determined whether Mars has its own biology would be one of the most consequential scientific mistakes in human history. It would permanently compromise our ability to answer the question of whether life on Mars originated independently from life on Earth. The astrobiologist Catherine Conley, who served as NASA's Planetary Protection Officer from 2006 to 2017, has been among the most vocal advocates for strengthening the international planetary protection framework before human missions reach Mars. Her argument is simple and compelling. Once humans land on Mars, the contamination question becomes essentially unanswerable. Human bodies carry trillions of microorganisms. A human crew cannot be sterilized the way a spacecraft can. The moment boots touch Martian soil, Earth biology is on Mars, permanently and irreversibly, which means that if we ever find microbial life in the Martian subsurface after human missions have landed, we can never be completely certain it did not hitchhike from Earth. This argues strongly for answering the life question definitively, or as close to definitively as possible, before human missions arrive. It is one of the most compelling scientific arguments for prioritizing sample return and subsurface exploration missions in the coming decade. Get the answer, or get as close to it as we can, before we contaminate the experiment. The geopolitical dimension adds another layer of complexity. China's space program, the the China National Space Administration, has been advancing at a pace that has genuinely surprised many Western analysts. The Tianwen-1 mission, launched in July 2020, successfully placed a spacecraft in Mars orbit, deployed a lander, and operated the Zhurong rover on the Martian surface, making China only the second country after the United States to successfully operate a rover on Mars. China has announced ambitions for Mars sample return missions and eventual crewed Mars exploration. Russia, the European Space Agency, the United Arab Emirates, Japan, India, all have active Mars programs or serious plans for them. Mars is becoming genuinely international in a way the Moon never was during the Apollo era. And that internationalization creates both opportunities and complications. The opportunity is shared resources, shared knowledge, shared cost. The complication is coordination, jurisdiction, and the possibility that competitive pressures, the same competitive pressures that drove the Apollo program, but also led to corners being cut and risks being taken, could push missions toward Mars before the scientific and ethical groundwork is fully laid. The history of exploration on Earth is not an encouraging precedent here. The encounter between technologically advanced civilizations and previously isolated ones has, more often than not, resulted in catastrophic harm to the less powerful party. Mars has no civilization to harm, but it may have life, and life, even microbial life, deserves a level of consideration that the history of exploration suggests we are not naturally inclined to give. These are uncomfortable thoughts. They are also necessary ones. The scientists and philosophers and ethicists who raise them are not anti-exploration. They are not trying to stop humanity from going to Mars. They are trying to ensure that when we go, and it does seem increasingly certain that we will go, we go thoughtfully, with our eyes open, with an awareness of what we might find and what we might do to it. Because here is the thing about terraforming that rarely gets said plainly. Terraforming Mars, if we do it, will be the single largest intervention any known intelligence has ever made in a planetary system. Larger than anything that has happened on Earth through human activity, comparable in scale to the geological and biological forces that shaped the planets themselves. We would be joining the roster of processes, volcanism, impacts, stellar evolution that determine the character of worlds, not as passive observers, as active participants. That is an extraordinary thing to contemplate, and it demands an extraordinary level of care. The astronomer and author David Grinspoon, in his 2016 book Earth in Human Hands, argues that humanity is already a planetary force on Earth, already changing atmospheric chemistry, ocean temperature, species composition, and land surface at a scale comparable to geological processes. He calls this the beginning of the Anthropocene, the age of humans as geological agents. His argument is that rather than retreating from this role, we should embrace it consciously, responsibly, and wisely. That the answer to being a planetary force is not to stop being one, but to become a better one. Applied to Mars, this argument suggests that terraforming, done carefully, done with full awareness of the ethical stakes, done in coordination with the best available science, is not an act of hubris. It is an act of responsibility, the responsibility of a species that has learned enough to know what it is doing and why. That is a beautiful argument. It is also a demanding one, because it requires us to be better than we have historically been, more patient, more humble, more willing to subordinate short-term gains to long-term outcomes, more capable of genuine cooperation across national and commercial boundaries, more honest about uncertainty, and more comfortable with questions that do not yet have answers. Whether we are capable of that, whether the species that has simultaneously produced the Hubble Space Telescope and thermonuclear weapons, the theory of evolution and genocide, the International Space Station, and the climate crisis, Whether that species can manage a project of the scale and ethical complexity of terraforming Mars responsibly is a question that no telescope can answer. It is a question about human nature, and the answer will be written not in the rocks of Mars, but in the choices we make here, on Earth, in the decades ahead. What we know is this: the science is real, the tools are developing, the missions are flying, the knowledge is accumulating. Every orbit of Maven, every rock drilled by curiosity and perseverance, every Marsquake measured by insight, every gram of oxygen produced by Moxie is a real contribution to a real body of knowledge about a real planet that real humans will one day visit and possibly, over centuries and millennia, transform. The universe spent 13.8 billion years making the conditions for this moment. For a species curious enough and capable enough to look at another world and ask, could we make it home? The question itself is remarkable. The fact that we have the tools to begin answering it, even partially, even provisionally, is one of the most extraordinary things about being alive right now, in this century, on this pale blue dot. And speaking of what we know right now, there is a specific body of research that has emerged in the past few years, focused on something called the Mars habitability window, that reframes the entire timeline of the terraforming question in a way that is both daunting and strangely hopeful. There is a concept in planetary science that does not get nearly enough attention outside of specialist circles. It is called the habitable zone, but not the one you are probably thinking of. Not the circumstellar habitable zone, that band of orbital distances around a star where liquid water can exist on a planet's surface. That one gets talked about constantly in the context of exoplanet research. The concept I am referring to is narrower, more specific, and in some ways more immediately relevant to everything we have been discussing. Scientists call it the planetary habitability window, the period in a planet's geological history during which its internal and external conditions align closely enough to support and sustain surface life. Earth is currently inside its habitability window, has been for roughly 3.5 billion years, will remain inside it for perhaps another billion years or so, before the sun's gradually increasing luminosity heats our planet beyond the point where complex life can persist. 1.5 billion years from now, Earth's oceans will begin evaporating. The habitability window will close, not abruptly, not all at once, but irreversibly. Mars had a habitability window too. Scientists believe it opened roughly 4 billion years ago when the planet was warm, wet, and magnetically shielded, and it closed relatively quickly in geological terms somewhere between 3.5 and 3 billion years ago, when the magnetic field collapsed and the atmosphere began its long, slow erosion. Mars's habitability window lasts perhaps 500 million to 1 billion years, long enough, conceivably, for simple life to have emerged and perhaps even diversified, but not long enough for anything like the complexity that Earth's much longer window has produced. The Mars habitability window concept matters for the terraforming conversation because of what it implies about the relationship between planetary history and planetary potential. Mars was not always outside its window. It was pushed outside by specific identifiable physical processes that in principle could be countered by sufficiently advanced engineering. Terraforming, viewed through this lens, is not the imposition of alien conditions on Mars. It is the artificial extension, or perhaps the artificial reopening, of a habitability window that closed prematurely. In 2024, a team of researchers at the Southwest Research Institute in San Antonio, led by the planetary scientist Dr. Simone Marchi, published modeling work in the journal Nature Geoscience that added important nuance to this picture. Their work focused on the timing and mechanism of Mars's atmospheric collapse in greater detail than previous models had achieved. using updated constraints from InSight's interior structure data combined with new isotopic measurements from Martian meteorites. What they found suggested that the collapse of Mars's magnetic field was not a single event but a gradual process, unfolding over several 100 million years, during which the planet's magnetic protection diminished intermittently rather than switching off all at once. This has a specific implication that is easy to miss. It means that even after the core dynamo began weakening, Mars retained partial magnetic protection for an extended period, perhaps long enough for life, if it had emerged during the earlier warm, wet phase, to adapt to progressively harsher conditions rather than being wiped out instantaneously. Life on Earth has repeatedly survived conditions that would have seemed impossible to an observer from outside: snowball Earth events, mass extinctions, dramatic atmospheric shifts. The resilience of biology, once established, is genuinely remarkable. If Martian life existed during the transition period that Marchi's team modeled, it had millions of years to find refugia, protected environments where conditions remained tolerable even as the surface became increasingly hostile. Those refugia almost certainly included the subsurface. And the subsurface, as we have established, is where the most credible hypotheses about present-day Martian life are concentrated. The connection between the new habitability window modeling and the subsurface life question is direct. If life had more time to adapt and migrate underground than previous models suggested, the probability of finding something alive down there today, in those brine pockets, those hydrothermal niches, those ancient cave systems, is correspondingly higher than it was previously estimated to be. We do not have the technology to explore Mars's deep subsurface right now. Our rovers scratch the surface, literally, drilling a few centimeters, occasionally a few tens of centimeters into the rock. The InSight heat probe, as we mentioned, failed to reach even 5 meters, reaching the depths where liquid water might exist. Potentially 1 to several kilometers down requires drilling technology that does not yet exist in a form deployable on Mars. On Earth, drilling to that depth is routine for the oil and gas industry, but Earth drilling rigs are enormous, require vast amounts of power, and depend on infrastructure, roads, supply chains, maintenance crews. That does not exist on Mars. Developing miniaturized, autonomous, nuclear-powered deep drilling systems for Mars is one of the most important technology challenges in planetary science right now. Several research groups and space agencies have been working on variations of this problem. The ice-penetrating cryobot concept, a heated probe that melts its way down through ice rather than mechanically drilling, has been developed primarily for exploring the subsurface oceans of Jupiter's moon Europa and Saturn's moon Enceladus, but the underlying technology is relevant to Mars as well, particularly for penetrating the polar ice caps to reach the subsurface liquid water detected by Marsis radar. A mission capable of drilling or melting its way to a Martian subsurface water body and sampling it directly, testing for microbial life with the sensitivity of a modern biochemistry laboratory, would be among the most consequential scientific missions in history. Its findings would not just answer the question of life on Mars, they would reshape our understanding of how common life is in the universe. Because if life arose independently on Mars, a planet in the same solar system formed from the same raw materials at roughly the same time as Earth, then the chemical pathway from non-living chemistry to living biology is clearly not vanishingly rare. It happens, perhaps it happens wherever the conditions allow. And the implications of that for the universe as a whole, for the billions of rocky planets orbiting billions of stars in our galaxy alone, are almost too large to hold in the mind. The famous Drake equation, developed by the radio astronomer Frank Drake in 1961 as a way of estimating the number of technologically communicating civilizations in our galaxy. includes a term called FEL, the fraction of planets with life that actually develop it, given the right conditions. Right now, we have exactly one data point for a FELV, Earth, where life arose relatively quickly after conditions allowed it. If Mars turns out to have life, or to have had it, that gives us a second data point. And in statistics, moving from one data point to two is not just an incremental improvement, it is a transformation. Two data points allow you to start drawing conclusions about a distribution, about how common something is, about whether it is the rule or the exception. The discovery of life on Mars, even fossilized, even microbial, even ambiguous, would be the most significant scientific finding in human history, bar none, more significant than the discovery of the Higgs boson, more significant than the detection of gravitational waves, more significant than any previous astronomical or biological discovery, because it would tell us something fundamental about the nature of life in the cosmos, about whether the universe is, at its core, a place that tends toward biology, or one in which Earth's biosphere is a statistical miracle, a fluke of almost impossible improbability in a vast and otherwise sterile void we do not know yet. And not knowing, sitting with that genuine, unresolved uncertainty, is one of the most intellectually honest and exciting places science can be. Now, let us bring this back down to something more tangible and immediate, because all of this philosophy and deep-time thinking, as necessary as it is, can sometimes obscure the very real, very practical, very human story of what Mars exploration and eventual habitation would actually feel like. Not in the abstract, not in the equations, but in the lived experience of the people who would actually be there. What would it be like to stand on Mars? We know enough now to answer this with reasonable fidelity. The sky famously is not blue. It is a butterscotch color during the day, a pale, pinkish orange that comes from fine dust particles suspended in the thin atmosphere, scattering sunlight differently than Earth's denser air does. At sunrise and sunset, the color scheme inverts in a way that is almost paradoxical. The sky near the sun glows blue, while the rest of the sky remains its characteristic reddish hue. Martian sunsets have been photographed by rovers, and they are genuinely beautiful, eerie and quiet, and unlike anything you would see from Earth. The sun looks smaller from Mars, roughly 2/3 the angular diameter it appears from Earth, because of the greater distance. Bright enough still to illuminate the landscape clearly, but dimmer. The light has a quality that astronauts and scientists who have thought about it describe as late afternoon, even at local noon, a slight dimness, a softness. As if the day is always edging toward evening, the silence would be profound. Mars has weather, wind, dust devils, occasional planet-girdling storms, but the thin atmosphere transmits sound poorly. A sound that on Earth would be clearly audible might be nearly inaudible on Mars at the same distance. The Perseverance rover carries a microphone, two, actually, and has recorded audio of the Martian environment. The first time sound from another planet has been captured and transmitted back to Earth. What it recorded was haunting, a thin, high-pitched wind, the whir of rover mechanisms sounding oddly muffled, and in one remarkable recording, the sound of the Ingenuity helicopter in flight, a rapid, insect-like buzzing that should have been clearly audible at that distance on Earth, but on Mars was barely perceptible even to sensitive microphones a few meters away. The atmosphere is that thin. The gravity you would feel, 38% of Earth's, would be genuinely strange in ways that are hard to intuit from a description. Not the dramatic floatiness of lunar gravity at 17%, something subtler. Things fall, visibly, clearly fall, but more slowly than you expect. Your body feels lighter. Your steps carry you slightly further than anticipated. Early Mars settlers would almost certainly develop a characteristic gait, adapting instinctively to the different gravitational environment. Athletes born on Mars might develop jumping and running capabilities that would look almost superhuman by Earth standards, though their bone and muscle development in lower gravity would make them poorly suited to visiting Earth in return. The radiation environment you could not feel at all, which in some ways makes it more unsettling. The galactic cosmic rays passing through your body are invisible, soundless, odorless. You would not know they were there, but they would be constantly, unavoidably, doing their slow work on your DNA. Early Mars settlers would likely carry personal radiation dosimeters and track their cumulative exposure the way workers in nuclear industries do on Earth. There would be career radiation limits, maximum lifetime doses that would effectively determine how long an individual could spend on the surface before being required to move to a more shielded environment underground. The isolation, the psychological weight of it, would be unlike anything most humans have experienced. On a clear night, Earth would be visible to the naked eye from Mars, a bright blue-white point of light, indistinguishable at first glance from a star. Everything you have ever known, everyone you have ever loved, your entire species, your entire civilization, your entire history, compressed into a single pixel of light. Some of the early Mars settlers would find that beautiful, a perspective-shifting reminder of the cosmic scale of the journey they had made. Others would find it unbearable. There is no predicting which. The Martian day, called a sol, is 24 hours, 39 minutes, and 35 seconds long. Close enough to Earth's day that human circadian rhythms would adapt relatively easily, though the slight lengthening would accumulate over time. Mars rover missions have long operated on Sol time rather than Earth time, and scientists who work on those missions describe the gradual drift of Mars time relative to Earth time, their waking hours slowly rotating through the Earth day, as one of the most disorienting aspects of the work. Living on Mars itself, in real Martian time, would eliminate that dissonance. Mars would become the reference. Earth time would be the foreign one. The seasons on Mars are longer than Earth's. The Martian year is approximately 687 Earth days, nearly 2 Earth years. The seasons are also more extreme than Earth's, because Mars's orbital eccentricity is much larger than ours. Its orbit is noticeably more elliptical, meaning it is significantly closer to the Sun at some points in its year than others. During Southern Hemisphere summer, Mars is near its closest approach to the Sun, making southern summers shorter but more intense. During Northern Hemisphere summer, Mars is further from the Sun, making northern summers longer and milder. This asymmetry has shaped the distribution of ice and dust across the planet in ways that planetary scientists are still fully working out. The dust. We have mentioned it in passing several times, but it deserves its own moment of attention. Martian dust is extraordinarily fine, particles just a few micrometers across, small enough to remain suspended in the thin atmosphere for months at a time during major storms. It is also potentially toxic. But the combination of fine particle size and perchlorate content means that Martian dust inhalation would be seriously dangerous to human lungs. Habitat designs for Mars settlements include elaborate airlock and dust mitigation systems, full-body cleaning procedures, sticky mats, electrostatic dust removers to minimize the amount of Martian dust that enters living spaces. Despite all precautions, some contamination would be inevitable. Managing chronic low-level perchlorate exposure in a human population is a medical challenge that Mars mission planners are taking seriously, and for which there are no good analogues in current medical practice. These are not minor inconveniences. They are genuine, serious challenges that a Mars settlement would need to solve, not once, but every day for every person, indefinitely. The romance of interplanetary exploration collides in these details with the relentless practicality of keeping living things alive in a place that wants to kill them. But that collision is also, in its own way, part of the story. Humans are extraordinarily good at adapting, at building systems, at learning from mistakes and improving. The people who figured out how to farm in the Sahara, how to survive Antarctic winters, how to live and work at the bottom of the ocean in research stations. Human adaptability across extreme environments has a track record that gives genuine grounds for cautious optimism. And cautious optimism, not naive enthusiasm, not paralyzing pessimism, but the specific, evidence-based, eyes-open optimism that comes from looking at both the obstacles and the tools honestly, is exactly the right frame for thinking about Mars, because the obstacles are real. We have been honest about them throughout this entire conversation. The magnetic field, the thin atmosphere, the radiation, the cold, the dust, the distance, the cost, the ethical questions, the political complexities, the sheer civilizational timescale of the project. None of these have been minimized or hand-waved away, but the tools are also real. Moxie works. Maven is teaching us exactly how the solar wind operates and how it might be countered. Insight has given us a map of Mars's interior that did not exist a decade ago. Perseverance is caching samples that could transform our understanding of Martian history and biology. Synthetic biology is advancing at a pace that was unimaginable a generation ago. Fusion power may be approaching practical reality. The computational tools for modeling planetary atmospheres are becoming more powerful and more accurate with every passing year. Nuclear thermal propulsion is being actively developed. The international interest in Mars, from a growing number of space agencies and private actors, means that the knowledge base and the engineering capability are expanding faster than at any point in history. The question is not whether the tools exist or will exist, they do or they will. The question is whether the will exists, the collective, sustained, intergenerational human commitment to a project that will not be completed within any single human lifetime. That kind of commitment is rare. It is not unprecedented. The great cathedrals of medieval Europe took generations to build, and the people who laid the first stones knew they would never see the spires completed. But it requires a cultural framework that values distant futures as much as immediate ones, a civilizational patience that does not come naturally to a species wired by evolution for short-term thinking. Developing that patience, cultivating the long view, the cosmic perspective, the ability to work toward goals measured in centuries, may itself be one of the most important things that the Mars project can give us. Not the terraformed planet, not the second home, but the practice of thinking on the timescale of worlds, of caring about what happens not just in our lifetimes, but in our descendants' lifetimes, and their descendants, and the descendants of people whose names and languages and cultures we cannot begin to imagine. That is what it means to take Mars seriously, not as a destination for adventure, not as a backup plan for a damaged Earth, but as an invitation to become the kind of species that deserves to spread among the stars, to earn the cosmos in some sense by demonstrating that we can be trusted with it. Are we that species yet? That is the honest question underneath everything else, and the answer right now is not entirely, but perhaps more than we were, and perhaps with the right choices, the right commitments, the right investments of both money and wisdom becoming more so. Carl Sagan, near the end of his life, wrote something that has stayed with me as the right note on which to orient everything we have been discussing. He wrote, "Every one of us is, in the cosmic perspective, precious. If a human disagrees with you, let them live. In 100 billion galaxies you will not find another." That fierce, tender, cosmic humility, the awareness of our rarity and our preciousness against the backdrop of the universe's unimaginable scale, is the spirit in which the best Mars science is done. Not conquest, not escape, but the expansion of what us means, the cautious, careful, wandering extension of the circle of life into a universe that, as far as we can tell, desperately needs it. Let us talk about what we actually know, not what we hope, not what we fear, not what makes for a good headline or a compelling tweet. What the evidence, taken seriously and read carefully, actually says about whether terraforming Mars is possible, and what the most honest answer to that question looks like when you strip away both the hype and the cynicism. The question, can we terraform Mars, is not one question. It is at least 4 separate questions, each with a different answer and a different timescale. Conflating them is the source of most of the confusion in public conversations about the topic. So let us separate them clearly and answer each one in turn. The first question is terraforming Mars physically possible in principle? Does the physics allow it? And the answer to this first question, based on everything we have covered across the past 8 parts of this conversation, is almost certainly yes. There is no law of physics that forbids warming a planet, thickening its atmosphere, shielding it from solar wind, and introducing biology that generates breathable gases over time. The processes involved, greenhouse warming, atmospheric accumulation, magnetic shielding, biological gas cycling, all operate on Earth and can in principle be engineered to operate on Mars. The physics is permissive. The universe does not say no. The second question is harder. Is it chemically and geologically possible, given what Mars actually has to work with? Does Mars contain the raw materials, the gases, the minerals, the water, the carbon that a terraforming effort would need? And here again the answer is encouraging, though with important caveats. Mars has carbon dioxide, enormous amounts of it, locked in the polar ice caps and the regolith. It has water ice at the poles in the mid-latitude subsurface, and possibly in much larger quantities in the deep subsurface than we currently know. It has nitrogen, less than we would ideally want, and nitrogen remains one of the genuine resource constraints on the project, but it is present. It has the minerals needed to produce synthetic greenhouse gases. It has perchlorates that, while toxic to humans, are a usable chemical resource. The inventory is not perfect, but it is workable. The third question is the one that stops most scientists cold. Is it technologically possible, given the tools we have, or can realistically develop? And this is where the answer becomes genuinely complicated. Because some parts of the technological challenge, producing oxygen on Mars, generating greenhouse gases, constructing pressurized habitats, building orbital mirrors, are within reach of foreseeable engineering development. We can see the path. The steps are steep, but they are identifiable. Other parts, particularly the magnetic shielding problem and the atmospheric retention problem over geological timescales, require technologies that do not yet exist even in prototype form and whose development timelines are genuinely uncertain. Decades, centuries. We cannot say with confidence. What we can say is that the direction of travel in the relevant technologies is encouraging, and that the pace of development in areas like synthetic biology, nuclear energy, and computational atmospheric modeling has consistently exceeded what pessimists predicted. The fourth question is the one almost nobody asks, even though it may be the most important of all. Is it wise? Should we do it even if we can? And this question does not have a scientific answer. It has an ethical one that depends on values, on what we believe we owe to other forms of life, to future generations, to the universe itself. We have circled around this question throughout our conversation, and I want to address it as directly as I can. The case for terraforming Mars, the strongest version of it, rests on several pillars. The first is survival. A multiplanetary species is harder to extinguish than a single planet one. The risks facing Earth, asteroid impacts, supervolcanic eruptions, pandemic-scale biological threats, and the long-term certainty of the Sun's expanding luminosity are real on astronomical timescales. A self-sustaining Mars civilization would not eliminate those risks for the humans on Earth, but it would ensure that some version of human civilization persisted even through a worst-case scenario. Insurance at planetary scale. The second pillar is knowledge. A terraforming effort would generate an enormous amount of scientific understanding about atmospheric chemistry, planetary geology, astrobiology, ecological engineering that would have applications far beyond Mars. The engineering solutions developed for Mars could inform how we think about managing Earth's own climate, which is increasingly a project we are engaged in, whether we plan to be or not. Learning how to deliberately shape a planetary atmosphere on Mars might teach us things we desperately need to know about the atmosphere we are inadvertently reshaping here at home. The third pillar is meaning. This is the least tangible and perhaps the most important. Human beings are not purely rational utility maximizers. We are storytelling creatures. We need narratives that give our existence significance beyond the merely biological. The story of becoming a multiplanetary species, of extending the reach of life and mind into the cosmos, is one of the most profound and motivating narratives available to a civilization that desperately needs something to work together on. The Apollo program at its peak engaged the creative and engineering energies of 400,000 people and inspired a generation. A sustained Mars civilization project with a terraforming goal at its horizon could do something similar and sustain it across generations rather than a decade. The case against, or more precisely, the case for caution, rests equally on strong ground. If Mars has life, the ethical calculus changes completely. You cannot terraform a living world without consequences for whatever is already living there. Even microbial life, even organisms that would look to a casual observer like nothing more than a smear of chemistry on a rock, would have an intrinsic value that demands consideration. They would be the product of billions of years of independent biological evolution. They would be, in the deepest sense, our equals in the story of life in the universe. Rendering their world uninhabitable, even in the process of making it habitable for us, would be an act that our descendants might judge very harshly. This is why the life question is not just scientifically interesting, it is ethically urgent. It needs to be answered before, not after, any large-scale planetary intervention begins. And here is where the most recent science becomes genuinely critical, because in 2023, a study led by Alexis Rodriguez at the Planetary Science Institute, published in Scientific Reports, provided new evidence for the existence of an ancient ocean on Mars, not just a network of rivers and lakes, as previously understood, but a large connected body of water in the northern lowlands, possibly persisting as recently as 3 billion years ago, longer than previously thought. This finding is significant for the life question because it extends the window during which Mars's surface could have been hospitable to life, and because it suggests the northern lowlands, a vast, relatively flat region that covers roughly a third of Mars's surface, may hold sedimentary records of that ancient ocean that have not yet been explored by any rover. None of our current or near-future rovers are targeted at the northern lowlands. Curiosity is in Gale Crater. Perseverance is in Jezero Crater. Both are in the southern hemisphere, chosen partly because the older terrain there is more likely to preserve ancient biosignatures. The potential sedimentary record of an ancient northern ocean is essentially unexplored. That represents an enormous scientific gap, and filling it should be among the highest priorities in Mars exploration planning. Now, let us do something we have not quite done yet in this entire conversation. Let us build the picture. Let us describe as concretely and as honestly as current science allows what a terraformed Mars might actually look like. Not the final, fully Earth-like version, which would take geological timescales to achieve, if it is achievable at all, But the intermediate state, the Mars of, say, 500 years from now, if humanity commits seriously to the project and the technology develops roughly as current trends suggest, 500 years is, by human standards, an almost incomprehensible span of time. 500 years ago, Leonardo da Vinci had just died. Europeans had recently reached the Americas. Copernicus had not yet published his heliocentric model of the solar system. The printing press was 50 years old. And yet, 500 years in the future is, in terms of the timescale of Mars transformation, relatively early in the project. In this 500-year scenario, the Mars of the 25th century looks like this. The average surface temperature has risen by roughly 20 to 30 degrees Celsius compared to today, through the combined effect of industrial greenhouse gas production, solar mirrors, and the partial release of frozen carbon dioxide from the polar regions. Average temperatures still run well below 0 Celsius across most of the planet, perhaps -20 to -40 Celsius on average, compared to today's -60. But the warmest regions, near the equator in summer, now regularly reach temperatures above freezing for significant parts of the day. The atmosphere is thicker. Not breathable, not even close. The pressure at the surface has perhaps doubled or tripled from today's roughly 600 pascals, reaching somewhere between 1,500 and 2,000 pascals. Still only about 2% of Earth's sea level pressure. Still instantly fatal to an unprotected human, but thick enough to slow the sublimation of ice, thick enough to allow liquid water to exist on the surface under the right conditions, thick enough to provide marginally more protection against radiation than the current near-vacuum liquid water. This is the change that everything else pivots on. In certain low-lying regions, ancient crater floors, the deep trenches of Valles Marineris, parts of the northern lowlands, seasonal liquid water now exists on the surface. Not oceans, not rivers yet, but transient pools, seasonal wetlands, frost that melts in the morning warmth and refreezes by evening. The planet is wet intermittently in a way it has not been for 3 billion years. In these wet zones, the first engineered organisms have taken hold. Hardy, perchlorate metabolizing bacteria, methane-producing archaea, primitive photosynthesisers, their pigments tuned by synthetic biologists to absorb the slightly reddish light that reaches Mars's surface. They are not visible to the naked eye, mostly, just a faint biological sheen on rock surfaces in the warmest areas, a slight darkening of soil that is biological rather than geological. But they are there, working, breathing out gases that accumulate in the atmosphere, fixing nitrogen, breaking down perchlorates, very slowly, imperceptibly slowly on any human timescale, beginning the work of making Mars more like a world that could eventually support complex life. The human population of Mars in this scenario is perhaps a few tens of thousands, concentrated in a handful of major settlements, pressurized underground complexes, lava tube habitats, and some purpose-built surface structures with heavy radiation shielding. Settlements named, perhaps, after the people and missions that made them possible: a city called Lowell, a research station called Sagan, a mining complex called Opportunity in memory of the rover that outlasted all expectations. These are not cities in any Earth sense. They are more like the early Antarctic research stations or the early outposts of the American West. Functional, frontier, with all the hardship and all the extraordinary communal intimacy that frontier life produces. The settlers of this Mars know they are not building for themselves. They are building for their grandchildren's grandchildren's grandchildren. They are the first stones of a cathedral they will never see completed. And that knowledge, sitting with it, living inside it, letting it shape how you spend your days, requires a particular kind of person. Not a hero in the conventional sense, something quieter and more durable, someone with the patience to plant trees in whose shade they will never sit, and the wisdom to find meaning in the planting itself rather than waiting for the shade. The politics of this 25th century Mars would be fascinating and completely unpredictable from our current vantage point. Just as the American colonies developed political identities and ultimately governing philosophies distinct from their European origins, Mars settlements would develop their own politics, shaped by the specific conditions of Martian life in ways we cannot foresee. The dependence on shared infrastructure, air, water, power, food production, in an environment where individual self-sufficiency is impossible, would create strong pressures toward collective governance and shared resource management. But the frontier mentality, the independence that comes from physical distance from established authority, would push equally strongly in the other direction. The political philosophy of Mars would be its own creation, and it would probably surprise everyone on Earth. The relationship between Earth and Mars, in legal terms, in economic terms, in cultural terms, would be one of the great geopolitical questions of that era. The tyranny of distance argument, the idea that a community separated from its governing authority by months of travel time and up to 44 light minutes of communication delay cannot meaningfully be governed from that authority, was one of the driving arguments for American independence from Britain. It will apply at least as forcefully to Mars. The first Martian independence movement is not a science fiction scenario. It is a political inevitability if Mars becomes sufficiently populated and self-sufficient. What form it takes and how Earth responds will be one of the defining stories of the coming centuries. And beneath all of this, beneath the politics, the engineering, the biology, the ethics, there is the simple human reality of people living on Mars, eating food grown in soil that their engineers spent decades making viable. Watching Martian sunsets from pressurized observation domes, that eerie blue glow around the sun that no human eye had ever seen before the first landers arrived. Teaching their children about Earth the way we teach our children about ancient history, with respect and connection, but also with the dawning awareness that this here now is home, that the red rock under their feet is as much their birthright as anything that came before. The children born on Mars will be the most important generation in this story, not because of what they do, though what they do will matter enormously, but because of what they represent. The proof of concept, the demonstration that human life, in all its fragility and stubbornness and creativity, can take root somewhere other than the world it evolved on, that the story of life in our solar system does not have only one chapter. When the first child takes their first steps on Martian soil, or more likely on the pressurized floor of a Martian habitat, something will have changed in the universe, irreversibly and permanently. Life will have reached, for the first time in 4 billion years of Earth's biological history, beyond the world that made it, and the cosmos, which spent 13.8 billion years building up to that moment through the patient accumulation of stars and planets and chemistry and time, will have taken one more step in whatever it is becoming. We are, all of us, part of that story. The scientists who design the missions, the engineers who build the hardware, the policymakers who fund the programs or fail to fund them, the students who study planetary science today and will lead the field in 30 years, the taxpayers whose money flows into space agencies, the citizens who vote for leaders with long or short horizons. Every one of us is a participant in the decision about what kind of future humanity is building toward. Whether we think about it or not, whether we want to be or not, the universe gave us curiosity. It gave us opposable thumbs and pattern recognition, and the ability to ask, what if, and then go find out. It gave us the audacity somewhere in our 4 billion year biological history to look up at the stars and imagine going there. That is not an accident, that is. in whatever sense the word applies to a universe without obvious purpose, an invitation. Whether we accept it and how we do so is entirely up to us. Here is the thing about big questions. The really big ones, the ones that span centuries, that involve entire planets, that touch on the deepest uncertainties about life and intelligence and the nature of the cosmos. Those questions have a way of folding back on themselves, of becoming, at their core, questions about the people asking them, about you, about what you believe, about what kind of future you are willing to imagine and work toward and, if necessary, sacrifice for. Can we actually terraform Mars? Started 10 parts ago as a question about planetary science, about magnetic fields and atmospheric pressure and greenhouse gases and synthetic biology. And all of that, every technical detail, every mission result, every equation has been real and necessary and worth understanding. But here, at the end, the question has quietly transformed into something else, into who are we as a species, and what are we capable of becoming? That transformation is not a retreat from science into philosophy. It is what happens when you follow the science honestly all the way to its conclusions. Because the science, followed honestly, leads you to a place where the limiting factor is no longer physics or chemistry or engineering. It is will, character, vision, the capacity to care about something larger than your own lifetime. And that is where you come in, not abstractly, not as a member of a faceless civilization. You, specifically, the person watching this right now, at whatever point in history you are watching it from, with whatever specific combination of skills and interests and circumstances you bring to this moment, because the decisions that will determine whether humanity becomes a multiplanetary species and whether any version of terraforming Mars ever begins are not going to be made by a small group of visionaries in isolation. They are going to emerge from the aggregate of millions of individual choices, commitments, and priorities made by people like you over the coming decades. Some of those choices are large and obvious. Going into planetary science, or aerospace engineering, or synthetic biology, or international space law, working on nuclear fusion or advanced propulsion, or closed-loop life support systems. Running for office with a long horizon view of what public investment should be building toward. These are real paths, and they matter enormously. But most of the choices that will shape this future are smaller and less obvious. They are choices about what you pay attention to, what you find worth understanding, what you talk about with the people around you, what you signal through your attention, your enthusiasm, your curiosity, that you value. Science does not happen in a vacuum. It happens in a cultural context. It is funded or defunded based on what a society decides to care about. Missions get approved or cancelled based on whether the political will exists to sustain them. The political will exists when the public cares. The public cares when the story has been told compellingly enough, often enough, by enough different voices, that it becomes part of the cultural conversation in a real way. That is what science communication is for, not just to inform, to cultivate, to build the constituency of people who understand enough to care and care enough to act. Every person who watches a video like this one and comes away genuinely engaged, genuinely curious, genuinely moved by the scale of what is possible is one more person in that constituency. One more voice that might, in some small but real way, tip a conversation, influence a decision, inspire a student, or shift the Overton window of what humanity considers worth attempting. You are not a passive observer of this story. You are a participant in it, right now. Whether you choose to be or not, let us come back one final time to the central question and give it the most direct, honest answer the evidence allows. Can we actually terraform Mars? The answer is probably yes, in stages, over timescales that stretch from decades to millennia, with technologies that are either already in development or clearly within the trajectory of foreseeable scientific progress, provided we do not find life there first, provided we build the international legal and ethical frameworks the project requires, and provided we develop the civilizational commitment and patience that a project of this scale genuinely demands. That probably yes is not a guarantee. Science does not deal in guarantees. It deals in probabilities, in evidence, in the best current understanding of how reality works, understanding that changes as new data arrives. And new data will arrive. The coming decade of Mars missions, including whatever emerges from the currently complicated Mars sample return effort, including potential new subsurface exploration technologies, including the continued work of Perseverance and any rovers that follow it, will tell us things we do not currently know that will refine this answer in ways we cannot fully predict. Maybe the samples come back and there is unambiguous evidence of ancient microbial life in the Jezero crater delta sediments. That finding would not end the Mars conversation, it would transform it. It would force a global reckoning with questions we have only begun to develop the ethical vocabulary for. What do we owe to the remnants, or the living descendants, of a biology that arose independently from our own? Is there a version of planetary stewardship, protecting and studying Martian life, building settlements that minimize ecological impact, eventually fostering rather than replacing the native biology, that is compatible with human habitation of Mars? Some astrobiologists think yes. Others think the very presence of human beings on Mars, with their cargo of Earth microorganisms, makes true coexistence impossible. This debate has not been resolved, and it will not be resolved until we know whether there is something to coexist with. Maybe the magnetic shielding technology develops faster than current timelines suggest, perhaps driven by fusion power breakthroughs that make high-energy electromagnetic systems cheap and practical in ways they are not today. In that scenario, the atmospheric retention problem, the problem that has seemed, to many researchers, like the hardest fundamental obstacle, becomes tractable within a century rather than several. The timeline compresses. The project that looked like a 1,000-year undertaking begins to look like a 500-year one. Maybe the synthetic biology advances of the coming decades produce organisms so well adapted to Martian conditions, so capable of surviving radiation, metabolizing perchlorates, producing warming gases, and building soil chemistry, that the biological phase of terraforming moves faster than any current model predicts. Life, after all, has a way of exceeding our models. It found a way into hydrothermal vents on the deep ocean floor, into the ultra-dry cores of the Atacama Desert, into the frozen lakes of Antarctica, into the cooling ponds of nuclear reactors. Designed life, with the full toolkit of synthetic biology behind it, might find ways into Martian niches that we cannot currently imagine, or maybe the challenges prove harder than they appear. Maybe the subsurface water bodies turn out to be less extensive than Marsist data suggests. Maybe the nitrogen deficit is more severe than current estimates. Maybe the psychological and physiological toll of long-duration Mars habitation turns out to have hard limits we have not yet discovered. Maybe the political and financial will to sustain a multi-generational planetary project proves impossible to maintain in a world dealing with its own enormous terrestrial challenges. These are not hypothetical concerns, they are real possibilities, and honest engagement with them is part of what makes the question worth taking seriously. The history of ambitious human projects is a history of being surprised in both directions. The Apollo program was declared impossible by serious engineers until it was not. The Human Genome Project was expected to take decades and was completed ahead of schedule and under budget. The eradication of smallpox, the deliberate extinction of a disease that had killed hundreds of millions of human beings, was accomplished through coordinated global effort in a generation. These things happened because enough people believed they were worth doing and put their energy and intelligence behind them. On the other side, fusion power has been 30 years away for 60 years. Cures for many diseases that seemed imminent a generation ago remain elusive. Global cooperation on climate change has proven far harder to sustain than the science requires. The gap between what is physically possible and what human institutions actually manage to accomplish is real and persistent and cannot be wished away. Mars will be somewhere in that space. Not as easy as the optimists insist, not as impossible as the pessimists claim. Somewhere in the vast, complicated, frustrating, magnificent middle ground where most of human history actually happens, where progress is real but slow, where setbacks are genuine but not final, where the story is always longer and stranger and richer than any single narrator can capture. What I want to leave you with, the thing I hope has come through in every part of this conversation, is not a conclusion but a disposition, a way of holding this question, open enough to accommodate uncertainty, rigorous enough to insist on evidence, humble enough to acknowledge the ethical weight of what we are contemplating, and hopeful enough, not naively but genuinely, based on what the science actually says, to believe that this is worth caring about, worth understanding, worth fighting for, in whatever arena you find yourself in. Carl Sagan looked at the first image of Earth from deep space, the one Voyager took in 1990, with our planet reduced to less than a single pixel of light against the vast darkness, and he wrote, "Look again at that dot. That's here, that's home, that's us." He was not writing about small-mindedness or despair. He was writing about the fragility and the preciousness of everything we have on this one small world, and implicitly about the responsibility we carry as the only known species in the universe capable of understanding its own cosmic situation, to take that situation seriously. Taking it seriously means protecting what we have here. It means addressing the planetary scale challenges we face on Earth with the same seriousness and urgency that Mars deserves. It means not treating Mars as an escape hatch from problems we should be solving at home. Earth is not disposable. It is the only place in the known universe with a biosphere billions of years in the making. The same wisdom that would make us good planetary stewards of Mars is the wisdom we need desperately right here. But taking it seriously also means looking outward, asking the questions that do not have comfortable answers, refusing to accept the implicit assumption that Earth is all there is or all there ever has to be, holding in mind simultaneously the fragility of what we have and the possibility of what we might become. That double vision, inward and outward at once, is not a contradiction, it is the whole point. You live in the century when the decision gets made, not the decision about terraforming, that is centuries away if it ever comes, but the decision about whether humanity goes to Mars at all, whether we build the knowledge base, the technology, the institutions, and the cultural commitment to make the larger journey possible. Whether the first chapter of the multiplanetary story gets written in this century or gets delayed another 100 years, or whether it never gets written at all. That decision is being made right now in budget committees and research laboratories and engineering firms and government agencies and university departments and startup companies and public conversations, in the questions that young people choose to ask and the careers they choose to pursue and the politicians they choose to support and the scientific literacy they choose to cultivate, in small ways and large ways, continuously, by millions of people, most of whom are not thinking about Mars at all, but whose choices accumulate into the conditions that either make this future possible or foreclose it. You are one of those people. You have just spent the time to learn something real about one of the most consequential questions humanity faces. That is not nothing. In fact, in a world awash in distraction and noise, it is actually quite rare and quite valuable. The next step is yours to determine. Maybe it is sharing what you have learned with someone who would find it interesting. Maybe it is digging deeper, picking up one of the books or papers we have referenced and following the thread further than a video can take you. Maybe it is reconsidering what career path you want to pursue, or what subjects you want to study, or what kind of work you want your life to have been about. Maybe it is simply carrying the question with you, letting it sit in the back of your mind, asking how it connects to other things you encounter, allowing it to slowly expand the frame through which you understand the universe and your place in it. All of that matters. All of it contributes to the culture in which these decisions get made. You are not separate from this story. You are part of it. Right now, in this moment, the atoms in your body were forged in dying stars. The curiosity in your mind is the universe's most extraordinary known achievement. Matter that has become aware of itself, that asks questions about its own origin, that imagines futures that do not yet exist, and then works to make them real. You are, in the deepest and most literal sense, stardust with the capacity to dream. And one of the things that stardust is dreaming about, has been dreaming about in various forms since the first human looked up at that red wandering light in the night sky and wondered what it was, is the possibility that we might one day go there, make it home, turn it from a cold, silent, rust-colored world into something living, something breathing, something that carries in its transformed skies and its engineered soils and its pressurized valleys and its eventual blue oceans, the unmistakable signature of minds that dared to try. Whether that dream becomes real depends on 1,000 things we cannot fully control and a handful of things we can. The science is real. The tools are developing. The knowledge is accumulating. The window, not Mars's habitability window, but humanity's window, is open right now. What we do with it in this century, in these decades, in these years, will echo across timescales we can barely imagine. So look up tonight if the sky is clear. Find Mars, that steady reddish point of light, not twinkling like a star, holding its light calm and constant in the dark. And know that what you are looking at is not just a planet, it is a question. The most important question our civilization is currently capable of asking. And you, standing there looking up at it, are exactly the kind of being the universe needed to produce in order to ask it. The story is not finished. It is barely started, and you are in it. And if everything we just covered lit something up in you, the next video is already on your screen. We explore the harsh reality of actually living on Mars. Dreaming about terraforming a planet is one thing. Surviving on it, that is a completely different story. Click it. You need to see this.